Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic history. Each episode here isn't just about stars. It's about the stories they hold, the quiet mysteries of power and scale, and the gentle questions that help us find our place. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. What is the most powerful thing in the universe? The question sounds simple enough, almost childlike in its directness. But the moment you begin to think about it seriously, the answer fragments into countless possibilities, each one compelling in its own way. Is power measured by the brightest flash of light, the strongest gravitational pull, the most violent explosion? Or is it something quieter, more persistent, a force that shapes everything over billions of years without fanfare or drama? The universe contains phenomena so energetic they defy human comprehension. A single supernova can outshine an entire galaxy for weeks. Black holes warp spacetime so severely that they trap light itself. The sun, that familiar orb in our sky, releases more energy every second than all of human civilization has produced in its entire history. And yet, the sun is merely average among stars, neither particularly large nor especially bright. Beyond individual objects lie forces, gravity, holding galaxies together, electromagnetism creating light and structure, nuclear forces binding atoms, and mysterious components like dark matter and dark energy that we cannot see but know must exist. When we ask about the most powerful thing, we are really asking several questions at once. Do we mean the strongest force, measured in how much it can push or pull? Do we mean the largest energy release, counted in the number of joules expelled per second? Do we mean the most dominant influence, the thing that shapes the universe more than anything else? Each interpretation points toward different answers. Gravity is weak between individual particles, but overwhelming across cosmic distances. The strong nuclear force is immensely powerful, but operates only within atomic nuclei. Dark energy seems to dominate everything, yet its effects are subtle and spread across billions of light years. The question becomes more complicated when we consider scale. At the quantum level, particles interact through forces we never directly feel. At human scales, gravity keeps us grounded and electromagnetism shapes our world. At stellar scales, nuclear fusion powers the light we see. At galactic scales, dark matter provides the gravitational scaffolding. At cosmic scales, dark energy accelerates expansion. Power shifts depending on where you look and what you measure. There is no universal yardstick that applies equally to a photon and a galaxy cluster. And then there is time. Some displays of power are instantaneous, a gamma-ray burst lasting only seconds, but releasing more energy than the sun will produce in 10 billion years. Others are steady and enduring, a star shining for eons, dark energy pushing on space for all eternity. Which is more powerful, the brief explosion or the eternal pressure? The question forces us to think not just about intensity but about persistence, not just about force but about consequence. Perhaps the impossibility of the question is precisely what makes it worth asking. It invites us to tour the universe's extremes, to visit places where matter is compressed beyond imagination, where energy flows at rates that dwarf anything we know, where the fabric of space and time itself bends and stretches. It asks us to think about what power really means. Is it the ability to destroy, to create, to shape, to endure? Each answer reveals something different about the cosmos and about the limits of our understanding. As you settle into this journey tonight, consider where you are. Perhaps you're lying in bed, ready to let these thoughts carry you gently towards sleep. Perhaps you're sitting quietly, winding down after a long day. Wherever you are, you exist within a universe governed by these very powers we're about to explore. The gravity that holds you to your bed, the electromagnetic forces that give your body structure, the nuclear reactions that created the atoms you're made of. All of these are parts of the story. The universe is not a simple place with simple answers. It is layered, complex, full of competing forces and influences. To explore the question of power is to explore the universe itself, from the smallest particles to the largest structures, from the earliest moments after the Big Bang to the distant future when stars have burned out and space has stretched thin. It is a journey through scale and time, through visibility and invisibility, through violence and silence. And so we begin with the impossible question, knowing that we may not arrive at a single answer. Instead, we will discover many answers, each one true in its own context. We will see that power in the universe is not one thing but many things, woven together in intricate patterns that have shaped everything we observe. The search for the most powerful thing becomes a search for understanding itself, an exploration of forces, energies, and phenomena that challenge our intuitions and expand our sense of what is possible. Tonight, we will visit stars being born and stars dying. We will peer into black holes where gravity reaches its ultimate expression. We will trace the invisible scaffolding of dark matter and the mysterious push of dark energy. We will examine the quantum realm where particles flicker in and out of existence, and we will look back to the Big Bang where everything began. Along the way, we will see that power takes many forms, some loud and obvious, others quiet and hidden, but all essential to the cosmos we inhabit. The impossible question is an invitation. It asks us to wonder, to compare, to think deeply about the nature of reality. It challenges us to move beyond our everyday experience and imagine forces and energies operating on scales that dwarf our world. And in that imagination, in that willingness to explore, we find a different kind of power. The power of curiosity, the power of thought, the power to ask questions that reach across billions of years and light years of space. So as we drift into this exploration, let the question itself be enough. What is the most powerful thing in the universe? We will discover that the answer is not simple, but that the search is rich with wonder. And perhaps that is the point, not to find a single answer, but to see the universe in all its powerful, beautiful complexity. Before we can compare supernovae to black holes, nuclear, forces to dark energy, or gravity to electromagnetism, we need to understand what we mean when we say power. In everyday language, the word carries many meanings. A powerful person might have influence or authority. A powerful emotion might move us deeply. A powerful storm might uproot trees and flood streets. But in physics, power has a precise definition that strips away ambiguity and gives us a tool for measurement and comparison. Power, in the language of physics, is the rate at which energy is transferred or transformed. It tells us not just how much energy is involved in a process, but how quickly that energy changes form or moves from one place to another. The distinction between energy and power is crucial. Energy is the capacity to do work, to move an object, heat a substance, emit light, or cause any kind of change. Power is the speed at which that work happens. Two systems can contain the same amount of energy, but if one releases it in a second and the other takes a year, their power outputs are vastly different. Think of it this way. Imagine holding a fully charged battery in your hand. Inside that battery is stored chemical energy, ready to be released. If you connect it to a small LED light, the battery might glow faintly for many hours, releasing its energy slowly over time. The power output is low, perhaps a fraction of a watt, but if you short-circuit that same battery, it could release all its stored energy in moments, heating up rapidly and perhaps even catching fire. The total energy is the same in both cases, but the power, the rate of energy release, is completely different. This distinction matters enormously when we compare cosmic phenomena. The sun contains vast amounts of energy locked in its hydrogen fuel. Over billions of years, it will convert that hydrogen into helium, releasing energy steadily through nuclear fusion. The total energy released over the Sun's lifetime is immense, but because that release happens slowly, spread across 10 billion years, the Sun's power output, while enormous by human standards, is modest compared to more violent events. A supernova, by contrast, might release a comparable amount of energy in just a few seconds. The power of that brief explosion dwarfs the Sun's steady glow, even though the total energy might be similar. In physics, we measure power in watts. 1 watt equals 1 joule of energy transferred or transformed per second. A joule itself is a small unit. Lifting an apple 1 meter against Earth's gravity requires about 1 joule of work. So 1 watt means doing that much work every second. A typical LED light bulb uses about 10 watts. A human body at rest requires roughly 100 watts to maintain its biological functions. A car engine might produce tens of thousands of watts. A large power plant generates billions of watts. And the Sun? It outputs approximately 3.8 times 10 to the 26th watts, a number so large that it loses meaning without context. The beauty of this definition is that it allows us to compare anything from the faintest flicker of a distant star to the most energetic explosion ever observed. As long as we can measure how much energy is involved and how quickly it's released or transformed, we can calculate power. This gives us a universal language for discussing everything from a light bulb to a gamma ray burst, from a human heartbeat to the expansion of the universe itself. Power also helps us understand efficiency and duration. A nuclear bomb releases energy in a fraction of a second, creating an enormous power spike. A star releases far more total energy over its lifetime, but spreads that release across billions of years. Which is more powerful depends on how you define the question. If you care about peak power, the maximum rate at any given moment, the bomb wins. If you care about sustained power over time, the star wins. Both measures are valid, but they tell different stories. This brings us to another important point. Power is not the same as force. Force is a push or pull that can cause acceleration, measured in newtons. Energy is the ability to exert force over a distance, measured in joules. Power is the rate at which that energy is used, measured in watts. All three concepts are related but distinct. A person pushing a heavy box across a floor exerts force. The work done force times distance represents energy, and how fast they push determines the power. Understanding these relationships helps us see why some phenomena seem powerful in one sense but not another. When we turn our attention to the cosmos, the numbers involved in power calculations become staggering. Stars, black holes, supernovae, and even the empty vacuum of space all involve energy transfers at rates that dwarf anything on Earth. To make sense of these numbers, scientists often use scientific notation, expressing values as powers of 10. The Sun's output of 3.8 times 10 to the 26th watts is easier to grasp when you realize it means 380, followed by 24 zeros. Even then, the scale is hard to visualize. It's roughly equivalent to the power output of 100 billion typical power plants running simultaneously. But power isn't always about big numbers. Sometimes, understanding power means understanding constraints and limits. The speed of light, for instance, sets an absolute limit on how fast energy can propagate through space. The laws of thermodynamics place restrictions on how efficiently energy can be converted from one form to another. And quantum mechanics introduces uncertainty at the smallest scales, affecting how we calculate energy and power in subatomic processes. These fundamental limits shape what kinds of power are possible in the universe. There's also the question of perspective. From our vantage point on Earth, the Sun seems immensely powerful, and it is powerful enough to drive our climate, power photosynthesis, and sustain all life on our planet. But from a cosmic perspective, the Sun is ordinary, perhaps even modest. Larger stars can be millions of times more luminous, radiating energy at rates that make our Sun look like a candle next to a searchlight. Context matters when we talk about power. As we move through this exploration, we'll return again and again to this definition. It's the lens through which we'll view everything from the strong nuclear force to dark energy, from stellar fusion to black hole collisions. Understanding power in this precise, measurable way allows us to move beyond vague impressions and make real comparisons. It gives us a foundation for asking which phenomena truly dominate the universe and which only seem powerful from our limited perspective. And so, with this definition in mind, power as the rate at which energy changes form or moves from place to place, we can begin our journey through the cosmos. We'll measure, compare, and marvel at the processes that shape reality at every scale. Some will be sudden and violent, others will be slow and persistent, but all of them, when examined through the lens of power, will reveal something profound about how the universe works. To understand power, the rate at which energy is transferred, we must first understand energy itself. Energy is one of the most fundamental concepts in all of physics, yet it's also one of the most abstract. Unlike matter, which we can touch and see, energy is something that exists in relationships and transformations. It's not a substance, but a property, a quantity that describes the capacity of a system to cause change, to do work, to influence the world around it. The remarkable thing about energy is that it appears in so many forms. There is kinetic energy, the energy of motion, a planet orbiting a star, a comet streaking through space, a particle racing through a detector. There is potential energy, stored in configurations and positions a rock, perched at the top of a cliff, a compressed spring, charged particles separated by distance. There is thermal energy, the random motion of atoms and molecules that we perceive as heat. There is electromagnetic radiation, energy carried by photons across the vacuum of space. There is nuclear binding energy, locked within atomic nuclei, released only through fusion or fission. Each form of energy can transform into others. A ball thrown upward converts kinetic energy into gravitational potential energy as it rises, then back into kinetic energy as it falls. A light bulb converts electrical energy into light and heat. A star converts nuclear binding energy into light and kinetic energy of particles. A black hole converts gravitational potential energy into radiation as matter falls toward it. These transformations happen constantly, at every scale, driving every process we observe. What makes energy truly special, what elevates it from a useful concept to a profound principle, is that it is conserved. In any closed system, the total amount of energy remains constant. Energy can change form, move from place to place, spread out or concentrate, but it can never be created from nothing, and it can never vanish into nothing. This law, the conservation of energy, is one of the most fundamental principles in physics, tested and confirmed in countless experiments across every domain of science. Think about what this means. Every bit of energy you encounter has existed since the beginning of the universe. The warmth you feel from sunlight was nuclear binding energy in the sun's core moments ago, converted through fusion into photons that travelled 93 million miles to reach your skin. Before that, it was gravitational potential energy in the collapsing cloud that formed the sun billions of years ago. Before that, it was part of the energy released in the Big Bang itself. Energy is never new. It only changes costume. The conservation of energy gives us a powerful tool for understanding the universe. If we can track where energy comes from and where it goes, we can predict how systems will behave. When a star runs out of hydrogen fuel, we know its energy output must drop unless another source like helium fusion takes over. When galaxies collide, we can calculate how their kinetic energy transforms into heat, light, and gravitational waves. Conservation means that energy is accountable, that we can follow its trail through every transformation. But conservation doesn't mean energy is equally useful in all its forms. This is where the second law of thermodynamics enters the picture, introducing the concept of entropy. While the total amount of energy remains constant, the quality of that energy, its ability to do useful work, tends to degrade over time. Heat disperses, Concentrated energy spreads out. Order gives way to disorder. A hot cup of coffee cools to room temperature, its thermal energy spreading into the surrounding air. That energy still exists, still obeys conservation, but it's no longer concentrated enough to be useful for heating something else. This principle has profound implications for the universe as a whole. All the energy that exists today existed at the Big Bang, but it was concentrated, organized, capable of driving dramatic changes. Over billions of years, as stars burn their fuel and galaxies spread apart, that energy disperses. The universe moves toward a state of maximum entropy, where energy is evenly distributed and no gradients exist to drive processes. This eventual fate, sometimes called heat death, is written into the nature of energy itself, a consequence of how transformations work. Energy also connects deeply to mass through Einstein's famous equation, E equals mc squared. This equation tells us that mass and energy are two aspects of the same thing, that matter itself is a form of concentrated energy. A small amount of mass can yield an enormous amount of energy because the speed of light squared is such a large number. This relationship is what powers nuclear reactions. When hydrogen fuses into helium in a star's core, a tiny fraction of the mass converts directly into energy. That small difference, multiplied by the speed of light squared, produces the light and heat that stars radiate for billions of years. The equivalence of mass and energy also means that energy can create matter. In particle accelerators, high-energy photons can transform into pairs of particles and antiparticles. In the early universe, when energies were extraordinarily high, such transformations were common. Matter and antimatter flickered in and out of existence, created from pure energy. As the universe cooled, this process slowed, but it left us with the matter we see today: protons, neutrons, electrons, all of it ultimately created from energy in the moments after the Big Bang. Understanding energy in all its forms allows us to see the universe as a vast network of transformations. Gravitational potential energy becomes kinetic energy as matter falls. Kinetic energy becomes thermal energy through friction and collisions. Nuclear binding energy becomes electromagnetic radiation through fusion. Electromagnetic radiation becomes chemical energy through photosynthesis. Chemical energy becomes mechanical energy in muscles. Every step is a transformation, governed by conservation, shaped by entropy, connecting everything to everything else. When we look at the night sky, we're seeing energy in motion. The light from stars is energy that left their surfaces years, centuries, or millennia ago. The cosmic microwave background is energy from the Big Bang itself, stretched and cooled by the expansion of space, but still traveling, still real, still part of the universal energy budget. Even the empty-seeming vacuum of space contains energy in the form of quantum fluctuations, and possibly a cosmological constant that drives the accelerated expansion we observe. Energy is both abstract and concrete, invisible, yet everywhere, conserved, yet always changing form. It's the currency of the cosmos, the quantity that accounts for every process, every motion, every transformation. To understand power, the rate of energy transfer, we must first appreciate energy itself in all its richness and complexity. And as we move forward in our exploration of the universe's most powerful phenomena, we'll see energy in every guise, concentrated in stars, released in explosions, hidden in dark components, flowing through space and time in patterns both simple and profound. Gravity is the first force most of us experience consciously. As children, we learn that things fall downward, that we cannot float away, that the ground is always there beneath us. This force seems so natural, so inevitable, that we rarely stop to think about how strange it really is. Gravity reaches across empty space without needing any medium to carry it. It pulls on every piece of matter in the universe, never pushing, never stopping, never resting. And though it is by far the weakest of the four fundamental forces, it shapes the cosmos more than any other. The weakness of gravity is genuinely startling when you examine it closely. If you pick up a paperclip with a small refrigerator magnet, the electromagnetic force between the magnet and the metal is strong enough to overcome the gravitational pull of the entire Earth. All 6 billion trillion kilograms of our planet pulling down on that paperclip, and a tiny magnet defeats it easily. The strong nuclear force is even more dominant, about 10 to the 38th power times stronger than gravity, at the scale of atomic nuclei. Even the weak nuclear force, which governs certain types of radioactive decay, is vastly stronger than gravity when comparing individual particle interactions. So why, if gravity is so weak, does it dominate the large-scale structure of the universe? The answer lies in two crucial properties. First, gravity is always attractive. Positive and negative electric charges can cancel out, leaving objects electrically neutral. Nuclear forces act only over tiny distances and can't reach beyond atomic nuclei. But gravity only pulls, never pushes, and every bit of mass attracts every other bit. There's no negative mass to cancel out positive mass. Second, gravity has infinite range. Its strength diminishes with distance, but it never completely vanishes. A galaxy on the other side of the universe exerts a tiny gravitational pull on you right now. It's unimaginably small, but it's there. These two properties mean that gravity accumulates. In a cloud of hydrogen gas floating in space, each atom pulls on every other atom. Individually, these pulls are negligible, but add up trillions upon trillions of atoms, and the combined gravitational attraction becomes significant. The cloud begins to contract. As it contracts, density increases and gravity strengthens. The process feeds on itself. Given enough mass and enough time, gravity inevitably wins, pulling matter together into stars, planets, and galaxies. This is how stars are born. Gravity gathers hydrogen and helium from the thin interstellar medium, concentrating it into clouds. Within those clouds, denser regions form, collapsing under their own weight. As the material falls inward, it heats up, pressure rising in the core. Eventually, if the mass is sufficient, temperatures reach millions of degrees, and nuclear fusion begins. At that moment, the energy released by fusion creates an outward pressure that balances gravity's inward pull. The star stabilizes, spending billions of years in this delicate equilibrium. Gravity built the star, and gravity holds it together against the outward blast of fusion. The same process operates on larger scales. Galaxies form because gravity pulls gas and dark matter into rotating disks. Clusters of galaxies form because gravity binds hundreds or thousands of galaxies together despite the vast distances between them. The cosmic web, the large-scale structure of the universe, with its filaments and voids, exists because gravity shaped the distribution of matter over billions of years. Everywhere we look, on every scale larger than individual atoms, gravity is the architect. Gravity also governs motion. Planets orbit stars because gravity bends their paths into ellipses. Moons orbit planets for the same reason. The moon's gravity raises tides on Earth, pulling on the oceans and even slightly deforming the solid rock beneath our feet. Comets trace long arcs through the solar system, their trajectories determined by the gravitational pulls of the sun and planets. Even light, though massless, bends in the presence of gravity because gravity curves space-time itself, and light follows those curves. This brings us to Einstein's revolution. Newton described gravity as a force acting at a distance, pulling objects toward each other. Einstein redefined it as the curvature of space-time. Mass and energy tell space-time how to curve, and the curvature tells objects how to move. This isn't just a philosophical distinction, it makes different predictions. Light bends around massive objects, not because gravity pulls on massless photons, but because the photons follow the curved geometry of space-time near those objects. Clocks run slower in stronger gravitational fields, not because something slows them down, but because time itself flows differently in curved space-time. General relativity has passed every experimental test thrown at it. We've observed light bending around the sun during eclipses. We've measured time dilation using atomic clocks at different altitudes. We've detected gravitational waves, ripples in space-time itself, produced by colliding black holes billions of light years away. Each confirmation strengthens our understanding that gravity isn't just a force pulling things together. It's the shape of the universe, the geometry of existence. At its most extreme, gravity creates black holes, regions where space-time curves so steeply that not even light can escape. These aren't just exotic curiosities. Most large galaxies, including our own Milky Way, harbour supermassive black holes at their centres, millions or billions of times the mass of the Sun. These giants influence how their host galaxies evolve, regulating star formation through the energy they release as matter falls into them. Gravity, in its ultimate expression, becomes so powerful that it transforms the very fabric of reality. Gravity also determines the fate of stars. When a star exhausts its nuclear fuel, gravity reasserts dominance. Without fusion to push back, the core collapses. For stars like our Sun, the collapse stops at the white dwarf stage, where electron degeneracy pressure provides support. For more massive stars, the collapse continues past that point, crushing matter into neutrons and forming neutron stars. For the most massive stars, nothing can stop the collapse, and black holes form. In each case, gravity drives the outcome, shaping the remnants that litter the galaxy. On the largest scale, gravity shaped the evolution of the entire universe. After the Big Bang, tiny quantum fluctuations in the density of matter were stretched to cosmic sizes. These fluctuations became the seeds of structure. Denser regions, with slightly stronger gravity, pulled in more matter. Less dense regions lost matter to their surroundings. Over hundreds of millions of years, gravity amplified these small differences into the galaxies and galaxy clusters we observe today. Without gravity, the universe would be a nearly uniform soup of particles, with no stars, no planets, no structures at all. Yet gravity is also fighting a losing battle on the larger scales. The expansion of the universe, now accelerating due to dark energy, works against gravity's pull. On scales larger than galaxy clusters, expansion wins. Galaxies that aren't gravitationally bound to each other are being carried apart by the expansion of space itself. In the distant future, as dark energy continues to dominate, gravity's ability to hold things together will be limited to smaller and smaller regions. But within those regions, within galaxies, within solar systems, within planets, gravity will remain the dominant force as it has been since the beginning. Gravity is quiet. It doesn't produce light or heat directly. It doesn't make noise. You can't see it or touch it. But its influence is everywhere, shaping every large structure in the universe, governing the motion of every celestial body, and ultimately determining the fate of stars, galaxies, and the cosmos itself. It is the first response to the question of power, because, despite its weakness at small scales, it is the force that built the universe we see. If gravity is the architect of cosmic structure, electromagnetism is the artist who paints the details. Gravity builds galaxies and stars. Electromagnetism creates atoms, molecules, light, and chemistry. It is responsible for nearly everything you can see, touch, or interact with directly. The colors of objects, the solidity of matter, the warmth of sunlight, the signals traveling through your nerves, all of these arise from electromagnetic forces. At the scale of atoms and everyday life, electromagnetism dominates, vastly stronger than gravity, shaping the material world in ways both obvious and subtle. Electromagnetism operates through electric and magnetic fields, two aspects of a single unified force. Electric fields surround charged particles, positive charges like protons, negative charges like electrons. Like charges repel each other, opposite charges attract. This simple rule explains the structure of atoms. The positively charged nucleus, packed with protons, attracts negatively charged electrons, holding them in orbit. At the same time, electrons repel each other, preventing them from collapsing into the nucleus. This balance creates stable atoms, the building blocks of all matter. The strength of electromagnetism compared to gravity is almost absurd. Between an electron and a proton in a hydrogen atom, the electric attraction is about 10 to the 39th power times stronger than their gravitational attraction. If gravity were the only force acting, atoms couldn't exist. There would be nothing holding electrons near nuclei. It's electromagnetism that gives atoms their size, their structure, and their chemical properties. Without it, there would be no chemistry, no molecules, no complexity beyond loose clouds of particles. Magnetic fields arise from moving charges. An electron spinning in its orbit, or electric current flowing through a wire, creates a magnetic field. These fields can exert forces on other moving charges, bending their paths, deflecting particles, and generating patterns of attraction and repulsion. Earth itself acts like a giant bar, magnet. Its magnetic field generated by currents of molten iron in its outer core. This field shields us from the solar wind, charged particles streaming from the sun that would otherwise strip away our atmosphere and bombard the surface with radiation. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single theoretical framework. His equations showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. Together, these oscillating fields can propagate through space as electromagnetic waves. The revelation was profound. Light itself is an electromagnetic wave. So are radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. They're all the same phenomenon, differing only in wavelength and frequency. The entire electromagnetic spectrum is a manifestation of this one force. Light carries energy from stars across the vacuum of space. Photons. The particles of light are massless but carry momentum and energy. When they strike your skin, they transfer that energy, warming you. When they enter your eyes, they trigger chemical reactions in your retina, allowing you to see. The sun's radiation, mostly visible light, and infrared drives photosynthesis in plants, powering the base of Earth's food chain. Without electromagnetic radiation, the energy generated in the sun's core would be trapped, unable to escape, and the universe would be dark. Electromagnetism is also what gives matter its solidity. When you touch a table, the reason your hand doesn't pass through it has nothing to do with the atoms being solid like billiard balls. Atoms are mostly empty space. What you're feeling is electromagnetic repulsion. The electrons in your hand's atoms repel the electrons in the table's atoms. These repulsive forces, acting over tiny distances, create the sensation of solidity. Every time you stand, sit, or hold something, you're experiencing electromagnetic forces preventing atoms from occupying the same space. Chemistry is nothing more than electromagnetism in action. Chemical bonds form when electrons are shared between atoms or transferred from one atom to another. The shapes of molecules, the strength of bonds, the reactivity of substances all depend on how electrons arrange themselves under the influence of electromagnetic forces. DNA, proteins, water, carbon dioxide, every molecule essential to life owes its structure to electromagnetic interactions. Life itself is a complex dance of electrons, guided by the push and pull of electric and magnetic fields. Humans have learned to harness electromagnetism in extraordinary ways. Generators use magnetic fields and rotating coils of wire to produce electric currents, powering cities. Motors reverse the process, using electric currents to create magnetic forces that drive motion. Radios and televisions transmit information by encoding it in electromagnetic waves. Medical, imaging technologies like MRI use powerful magnetic fields to peer inside the human body without surgery. Particle accelerators use oscillating electric fields to accelerate charged particles to nearly the speed of light, smashing them together to study fundamental physics. Electromagnetism also plays a critical role in astrophysics. When matter falls toward a black hole, it forms an accretion disk, superheated by friction and compression. This disk radiates electromagnetic energy across the spectrum, from radio waves to X-rays, allowing us to detect black holes even though they emit no light themselves. Pulsars, rapidly spinning neutron stars, emit beams of electromagnetic radiation from their magnetic poles, sweeping across space like cosmic lighthouses. Some of the most energetic phenomena in the universe, gamma-ray bursts, for instance, release more electromagnetic energy in a few seconds than the sun will emit in its entire lifetime. On Earth, electromagnetic forces are so ubiquitous that we barely notice them. The light from your screen, the electricity in your walls, the radio signals carrying data through the air, the chemical reactions in your cells all are mediated by electromagnetism. It's the force that makes the modern world possible, from the simplest light bulb to the most advanced supercomputer. Without it, technology as we know it couldn't exist. And yet, for all its strength and versatility, electromagnetism has limits. Because charges come in two types, positive and negative, large-scale structures tend to be electrically neutral. Planets, stars, and galaxies contain roughly equal amounts of positive and negative charge, so their electric fields cancel out over long distances. This is why gravity, despite being far weaker, dominates at cosmic scales. Electromagnetism's power is confined mostly to the atomic and molecular realm, where individual charges matter. Beyond that, gravity takes over. There is also the mystery of why electromagnetism has the strength it does. The fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions, is approximately 1/137. Why this value and not something else, no one knows. If it were slightly different, atoms might not be stable, chemistry would change, and life as we know it might not be possible. The strength of electromagnetism, like so many fundamental constants, seems finely tuned to allow the complexity we observe. Electromagnetism is a contradiction in the context of cosmic power. It is immensely strong, far stronger than gravity between individual particles, yet it remains largely invisible on the grandest scales. It creates all the richness of chemistry and light, yet it doesn't shape galaxies or govern the expansion of the universe. It is both everywhere and confined, both powerful and limited. Understanding this contradiction helps us see that power in the universe is not about one force dominating all others, but about different forces ruling different domains, each essential in its own way. Deep inside every atomic nucleus, in a space smaller than you can imagine, a force operates that dwarfs every other interaction in raw strength. This is the strong nuclear force, and it is responsible for holding the cores of atoms together against the intense electromagnetic repulsion between protons. Without it, atomic nuclei could not exist. Without atomic nuclei, there would be no elements beyond hydrogen, no chemistry, no stars that shine through fusion, and no material universe as we know it. The strong force is hidden from direct experience, confined to distances smaller than the nucleus itself, but its influence shapes everything. Protons carry positive electric charge. Pack two or more of them into the tiny volume of a nucleus, and electromagnetism screams that they should fly apart. The repulsive force between positively charged particles increases as they get closer together, and at nuclear distances, that repulsion is enormous. Yet nuclei hold together. Carbon nuclei contain 6 protons. Iron contains 26. Uranium contains 92. Something must be overpowering the electromagnetic force, binding these protons together despite their mutual repulsion. That something is the strong nuclear force. The strong force is aptly named. At the distances where it operates on the order of a femtometer, or 10 to the negative 15th meters, it is roughly 100 times stronger than electromagnetism. This makes it the strongest of the 4 fundamental forces by a significant margin. Its job is simple but essential. Hold quarks together to form protons and neutrons, and hold those protons and neutrons together to form atomic nuclei. It does both jobs with overwhelming strength, creating the stability that allows matter to exist. To understand the strong force, we need to look inside protons and neutrons. These particles, collectively called nucleons, are not fundamental. Each one is made of 3 smaller particles called quarks, held together by particles called gluons. Quarks come in different types, or flavors: up, down, strange, charm, top, and bottom. A proton consists of 2 up quarks and 1 down quark. A neutron consists of 1 up quark and 2 down quarks. The gluons that bind them are the carriers of the strong force, and they have a unique property. They interact with each other as well as with quarks. This self-interaction gives the strong force a strange character. Unlike electromagnetism, where the force weakens steadily as you separate charges, the strong force behaves differently. At very short distances, it's actually relatively weak, allowing quarks some freedom to move within a proton or neutron. But try to pull quarks apart, and the force grows stronger. The more you try to separate them, the harder the strong force pulls them back. This property is called confinement. Quarks are never found in isolation. They are always bound together in groups, forming composite particles. If you put enough energy into trying to separate 2 quarks, something remarkable happens. Instead of pulling them apart, you create new quark-antiquark pairs from the vacuum. These new particles immediately bind to the original quarks, forming new composite particles. It's as if the strong force refuses to let quarks exist alone, continually creating new particles to maintain confinement. This behavior is unique among the fundamental forces and arises from the mathematics of quantum chromodynamics, the theory describing the strong interaction. The strong force is what powers stars. In the core of a star like the Sun, temperatures reach about 15 million degrees Celsius. At these temperatures, hydrogen nuclei single protons move fast enough that occasionally, despite their electromagnetic repulsion, they get close enough for the strong force to take over. When they do, they can fuse together, forming heavier nuclei and releasing energy in the process. This nuclear fusion is the source of sunlight, the engine that has powered our star for nearly 5 billion years and will continue for another 5 billion. The energy released in fusion comes from a subtle difference in mass. When protons fuse to form helium, the resulting nucleus weighs slightly less than the sum of its parts. That missing mass has been converted into energy. Following Einstein's equation, E equals mc squared. Because the speed of light squared is such an enormous number, even a tiny amount of mass yields a tremendous amount of energy. The strong force, by binding nuclei together, creates the conditions for this mass-energy conversion. The same principle operates in nuclear fission, the process that powers nuclear reactors and atomic weapons. Heavy nuclei, like uranium or plutonium, are unstable. When struck by a neutron, they split into lighter nuclei, releasing energy and more neutrons. This happens because the strong force binds the fragments more tightly than it bound the original heavy nucleus. The difference in binding energy is released as kinetic energy and radiation, creating a chain reaction that can be either controlled in a reactor or unleashed in an explosion. The strong force also explains why elements heavier than iron are relatively rare. Fusion releases energy only up to iron. Beyond iron, fusing nuclei together requires an input of energy rather than releasing it. Because the strong force binds iron's nucleus so efficiently that adding more protons and neutrons actually creates a less stable configuration. Heavy elements like gold, uranium, and lead are created in supernova explosions or neutron star collisions, where extreme energies overcome this barrier. The strong force sets the boundary, determining which elements can be created in stars and which require more violent environments. Despite its strength, the strong force has essentially zero range. Beyond the nucleus, it operates over distances of about 1 femtometer, roughly the diameter of a proton. Beyond that tiny scale, its influence drops to nothing. This is why we don't feel the strong force in daily life. Electromagnetic forces operate over much larger distances, governing chemistry and material properties. The strong force remains hidden inside nuclei, invisible but indispensable. Theoretical physicists describe the strong force using quantum chromodynamics, or QCD, a mathematically rich and complex theory. In QCD, quarks carry a property called color charge, not related to visual color, but analogous to electric charge in electromagnetism. Gluons carry color charge too, which is why they interact with each other, creating the unique behaviors of confinement and asymptotic freedom, the weakening of the force at short distances. Solving QCD equations requires powerful supercomputers running lattice simulations, breaking spacetime into a grid, and calculating interactions step by step. The strong nuclear force is a hidden titan, operating in the smallest spaces, binding the matter that makes up stars, planets, and people. It is the strongest force nature has devised, powerful enough to overcome electromagnetic repulsion, to hold quarks in permanent confinement, to power the fusion that lights the stars. Without it, there would be no atomic nuclei beyond hydrogen, no chemical diversity, no sustained sources of stellar energy. It is invisible, confined, and absolutely essential, a giant hidden in the heart of every atom. Among the four fundamental forces, the weak nuclear force is the least familiar, the least intuitive, and in some ways the most difficult to explain. It doesn't hold things together like gravity or the strong force. It doesn't create light or structure like electromagnetism. Its range is even shorter than the strong force, and its strength, while not as feeble as gravity, is still modest compared to electromagnetism or the strong interaction. Yet despite these apparent limitations, the weak force plays a role so essential that without it, stars couldn't shine, elements couldn't form, and the universe would be a very different and far less interesting place. The weak force governs certain types of radioactive decay and enables transformations between different kinds of particles. While the strong force binds quarks and nucleons, and electromagnetism governs charged particles, the weak force allows particles to change identity. A neutron can decay into a proton, emitting an electron and an antineutrino. A proton can transform into a neutron under the right conditions, releasing a positron and a neutrino. These transformations, impossible under the other forces, are the signature of the weak interaction. One of the most important roles of the weak force is in stellar fusion. Consider the Sun. In its core, hydrogen nuclei protons collide at high speeds. Occasionally, two protons get close enough for the strong force to act. But there's a problem. Two protons cannot form a stable nucleus on their own. For fusion to proceed, one of the protons must transform into a neutron, creating deuterium, a stable isotope of hydrogen. This transformation is mediated by the weak force. Without it, the first step of the fusion chain would never happen, and stars like the Sun could not burn. This process is called beta plus decay, and it's extraordinarily slow compared to other nuclear reactions. The weak force's relative feebleness means that proton to neutron conversion happens rarely, which is actually essential for stars. If the weak force were stronger, fusion would occur too quickly, and stars would burn through their fuel in moments rather than billions of years. If it were weaker, fusion might not happen at all. The weak force's strength is finely balanced, allowing stars to burn steadily over immense timescales, creating the stable energy sources that make planetary systems and life possible. The weak force is also responsible for the existence of neutrinos, some of the most elusive particles in the universe. Neutrinos are produced in vast numbers during nuclear reactions in the cores of stars, in supernova explosions, in radioactive decay on Earth. They are nearly massless, carry no electric charge, and interact only through the weak force and gravity. This makes them extraordinarily difficult to detect. Trillions of neutrinos pass through your body every second, streaming from the sun and other sources, yet they almost never interact with your atoms. Detecting neutrinos requires enormous detectors filled with water or other materials, buried deep underground to shield them from other particles. When a neutrino does interact, it produces a tiny flash of light or a charged particle that can be detected. These rare events allow scientists to study processes happening in the cores of stars, in supernova, and even in the first moments after the Big Bang. Are messengers from places and times we cannot observe any other way, and their existence is a direct consequence of the weak force. The weak interaction also violates certain symmetries that the other forces respect. One of the most surprising discoveries in 20th century physics was that the weak force distinguishes between left and right. This property, called parity violation, means that the weak force behaves differently when viewed in a mirror. In certain radioactive decays, electrons are emitted preferentially in one direction rather than being evenly distributed. This left-right asymmetry was shocking when first discovered, challenging the assumption that the laws of physics should be the same regardless of orientation. Another profound role of the weak force concerns the matter-antimatter asymmetry in the universe. In the Big Bang, matter and antimatter should have been created in equal amounts. When matter and antimatter meet, they annihilate, producing energy. If the amounts had been perfectly balanced, everything would have annihilated, leaving only radiation. Yet here we are, in a universe made of matter. Something broke the symmetry. The weak force violates a symmetry called CP, charge parity symmetry, creating slight differences in the behavior of matter and antimatter. While the observed violation isn't large enough to fully explain the asymmetry, it provides a crucial clue that the weak force played a role in creating a matter-dominated universe. The weak force is mediated by particles called W and Z bosons, which are much heavier than the photon, which mediates electromagnetism, or the gluons, which mediate the strong force. The W boson has a mass about 80 times that of a proton. The Z boson is about 90 times as massive. This large mass is why the weak force has such short range, only about 1/1000th the diameter of a proton. It also explains why weak interactions are relatively rare. Creating these heavy bosons, even virtually in quantum processes, requires a lot of energy, making weak interactions much less probable than electromagnetic or strong interactions. In the 1960 seconds and 70 seconds, physicists discovered that the weak force and electromagnetism are actually two aspects of a single unified force called the electroweak interaction. At very high energies like those present shortly after the Big Bang, the distinction between electromagnetism and the weak force disappears. They merge into one. As the universe cooled, this unified force split into the two separate interactions we observe today. This unification was confirmed experimentally with the discovery of the W and Z bosons at CERN in 1983, a triumph of theoretical prediction and experimental verification. The weak force also plays a critical role in supernova. When a massive star's core collapses, protons and electrons are crushed together, forming neutrons and releasing vast numbers of neutrinos through weak interactions. These neutrinos carry away most of the energy from the collapse, and their interactions with the outer layers of the star help drive the explosion that we see as a supernova. Without the weak force, this mechanism wouldn't work, and the distribution of heavy elements across the universe would be very different. Radioactive decay, governed by the weak force, has practical applications on Earth. Carbon-14 dating uses weak decay to determine the age of archaeological artifacts. Radioactive isotopes used in medicine, like those in PET scans, decay through weak processes, emitting positrons that allow doctors to image the inside of the body. The heat from radioactive decay of elements like uranium and thorium in Earth's interior, also mediated by weak interactions, contributes to geological activity, driving plate tectonics and volcanic processes. The weak force is strange, subtle, and essential. It doesn't dominate any domain the way gravity rules galaxies or electromagnetism shapes chemistry. Instead, it enables transformations, creates diversity, and allows processes that would otherwise be impossible. It is the force of change, turning one particle into another, making stars burn slowly, filling the universe with neutrinos, and perhaps explaining why matter exists at all. Without it, the cosmos would be simpler, but also lifeless, a universe of hydrogen and helium, unable to build the complexity we see around us. Light is so familiar that it's easy to take for granted. We flip a switch, and a room floods with brightness. The sun rises, and the world transforms from shadow into colour. Yet light is one of the most profound phenomena in physics, a carrier of energy, a messenger across vast distances, and a window into the workings of the universe. Understanding light as energy in motion reveals not only its power, but also its central role in almost everything we observe and measure. In physics, light is electromagnetic radiation, oscillating electric and magnetic fields that propagate through space at the universe's ultimate speed limit, approximately 300,000 kilometers per second. Nothing with mass can travel this fast. Only massless particles like photons can reach and maintain this speed. Light's velocity is so fundamental that it appears in the structure of spacetime itself, defining the maximum rate at which information or causality can propagate. Light exists as both wave and particle, a duality that was one of the great revelations of quantum mechanics. As a wave, light has wavelength and frequency, properties that determine its colour in the visible spectrum, or its place along the broader electromagnetic spectrum. As a particle, light consists of photons, discrete packets of energy, each carrying an amount determined by its frequency. High-frequency light, like ultraviolet or gamma rays, carries more energy per photon. Low-frequency light, like radio waves, carries less. This wave-particle duality isn't a flaw in our understanding. It's the actual nature of light, behaving as waves in some experiments and as particles in others. The electromagnetic spectrum extends far beyond what our eyes can detect. Radio waves have wavelengths from meters to kilometers. Microwaves range from millimeters to centimeters. Infrared spans from about a micrometer to a millimeter. Visible light, the narrow band, our eyes evolved to see stretches from about 400 to 700 nanometers, from violet to red. Ultraviolet light has shorter wavelengths, followed by X-rays, and finally gamma rays, with wavelengths shorter than the size of atoms. All of these are fundamentally the same phenomenon, differing only in energy and wavelength. Each part of the spectrum reveals different aspects of the universe. Radio telescopes detect cold hydrogen gas between stars and the faint emissions from pulsars. Infrared observatories peer through dust clouds to see star formation hidden from optical view. Visible light shows us stars, galaxies, and the surfaces of planets. Ultraviolet light reveals hot young stars and active galactic nuclei. X-ray telescopes map superheated gas around black holes and neutron stars. Gamma-ray detectors capture the most energetic events in the cosmos, from supernova to gamma-ray bursts. Each wavelength is a different lens through which we view reality. Light carries energy across space without needing any medium. Sound requires air or water or solid material to propagate. It's a mechanical wave travelling through matter. But light can cross the vacuum of space, travelling for billions of years from distant galaxies to our telescopes. The photons reaching your eyes from a distant star left that star long ago, perhaps before humans existed, carrying their energy unchanged across the emptiness. This ability to travel through vacuum makes light the primary messenger from the cosmos. Almost everything we know about the universe beyond Earth comes from catching and analysing light. The energy carried by light can be absorbed, transformed, or redirected. When sunlight strikes your skin, photons are absorbed by molecules, which vibrate more rapidly. We perceive this as warmth. When light hits a solar panel, photons knock electrons loose, creating an electric current. When light enters your eye, it triggers chemical changes in photoreceptor cells, initiating the process of vision. In each case, electromagnetic energy converts into another form: thermal, electrical, or chemical. Photosynthesis is perhaps the most important example. Plants use light energy to drive chemical reactions, converting carbon dioxide and water into glucose and oxygen. This process powers nearly all life on Earth, capturing the sun's energy and storing it in chemical bonds. Animals eat plants, breaking those bonds to release the stored energy. Even fossil fuels, coal, oil, and gas, are ancient sunlight. Energy captured by photosynthesis millions of years ago, and now released through combustion. The energy you use every day traces back, in most cases, to light from the sun. Light also carries momentum, even though photons are massless. This seems paradoxical, but it's a consequence of relativity. When photons strike a surface, they exert pressure, a tiny push. On Earth, this pressure is too small to notice in daily life. But in space, with no air resistance and vast timescales, light pressure can move objects. Comets develop tails partly because photons from the sun push dust and gas away from the nucleus. Spacecraft designers have proposed solar sails, large reflective sheets that could be propelled across the solar system by the pressure of sunlight alone. Light can move matter, not through force in the traditional sense, but through the transfer of momentum. Stars radiate enormous amounts of energy as light. The sun outputs about 3.8 times 10 to the 26th watts, almost all of it as electromagnetic radiation. This energy originates in the core, where nuclear fusion converts mass into energy. Photons created in fusion reactions scatter through the sun's dense interior, taking tens of thousands of years to reach the surface. Once free, they travel across space at light speed, reaching Earth in just over 8 minutes. A tiny fraction of the sun's total output strikes our planet, but even that fraction is enough to drive our weather, sustain ecosystems, and make life possible. In the early universe, light played a different role. During the first few 100,000 years after the Big Bang, the cosmos was opaque, a hot, dense plasma, where photons scattered constantly off free electrons. Light couldn't travel far. It was trapped in a fog. As the universe expanded and cooled, electrons combined with protons to form neutral atoms. This moment, called recombination, allowed photons to travel freely for the first time. Those photons are still traveling today, stretched by the expansion of space into microwaves. This cosmic microwave background is a snapshot of the universe at age 380,000 years, carried to us by light that has journeyed for nearly 14 billion years. Light allows us to measure distance and time in astronomy. By analyzing how light shifts to longer wavelengths, redshift, when its source moves away, we can determine the velocities and distances of galaxies. By measuring the brightness of certain types of supernovae, which have known luminosities, we can calculate how far away they are. Light curves, how an object's brightness changes over time, tell us about the physics of explosions, the orbits of binary stars, and the presence of planets around other stars. Light is data, carrying encoded information about temperature, composition, velocity, and more. There are also stranger aspects of light tied to quantum mechanics. Photons can be entangled, linked in ways that defy classical intuition. Measuring one photon state instantly affects the state of its entangled partner, even if they're separated by large distances. This phenomenon has been experimentally verified and is now being explored for quantum communication and computing. Light, even at the quantum level, reveals depths of behavior that challenge our understanding. Light is energy in motion, pure, fast, and versatile. It fills the universe, carries information across incomprehensible distances, drives the chemistry of life, and provides nearly all our knowledge of the cosmos. From the faintest glow of a distant galaxy to the brilliant flash of a nearby lightning bolt, light connects everything. Understanding its nature and behavior is essential to understanding the universe itself. It is power made visible, energy given wings, the medium through which the cosmos reveals its secrets. When you look up at the night sky, every point of light you see, except the planets, is a star, a self-sustaining fusion reactor converting hydrogen into helium and releasing energy in the process. Stars are nature's power, plants running for billions of years on nuclear fuel, flooding space with light and heat. They are the engines that illuminate the universe, and without them, there would be no elements beyond hydrogen and helium, no planets, and no life. Understanding stars means understanding one of the most fundamental and powerful processes in the cosmos: nuclear fusion. Stars begin their lives in clouds of gas and dust scattered through galaxies. These molecular clouds, sometimes spanning hundreds of light years, are cold and dark. But within them, gravity is always at work. Small density fluctuations, regions slightly denser than their surroundings, begin to attract more material. As gas falls inward, the region grows denser and hotter. Gravitational potential energy converts to thermal energy. If enough mass accumulates, temperatures in the core eventually reach millions of degrees. At that point, nuclear fusion ignites and a star is born. Fusion is the process of combining light atomic nuclei into heavier ones, releasing energy in the process. In stars like our Sun, the dominant reaction is the proton-proton chain, where hydrogen nuclei single protons fuse to form helium. This happens in stages. First, two protons collide, and through the weak nuclear force, one transforms into a neutron, creating deuterium, a hydrogen isotope with one proton and one neutron. Then, another proton fuses with the deuterium, forming helium-3, two protons and one neutron. Finally, two helium-3 nuclei combine to form helium-4, two protons and two neutrons, releasing two protons in the process. Each step releases energy. The source of that energy is mass. The helium nucleus produced weighs slightly less than the sum of the hydrogen nuclei that went into it. This missing mass hasn't disappeared, it's been converted into energy, following Einstein's equation E equals mc squared. Because the speed of light squared is such an enormous number, even a tiny amount of missing mass yields tremendous energy. In the Sun's core, about 600 million tons of hydrogen are converted into helium every second, and about 4 million tons of matter are converted directly into energy. This energy is released as photons and neutrinos. The photons scatter through the Sun's dense interior, bouncing from particle to particle, gradually working their way outward. This random walk can take tens of thousands of years, but once a photon reaches the surface, it streams freely into space at light speed, reaching Earth in just over 8 minutes. The neutrinos, which interact only weakly with matter, escape the core almost immediately, carrying information about the fusion reactions directly to detectors on Earth. The balance between gravity and fusion pressure is what makes a star stable. Gravity pulls inward, trying to collapse the star. Fusion generates heat and pressure, pushing outward. For most of a star's life, these forces are in equilibrium. The star neither collapses nor explodes. It simply shines. This phase, called the main sequence, lasts for billions of years for stars like the Sun. The larger the star, the faster it burns its fuel, and the shorter its main sequence life. Small red dwarfs can burn for trillions of years. Massive blue giants exhaust their hydrogen in just a few million years. When a star runs out of hydrogen in its core, the balance shifts. Without fusion to provide outward pressure, the core contracts under gravity, heating up further. This can ignite helium fusion, where 3 helium nuclei combine to form carbon in a process called the triple alpha reaction. Stars like the Sun will reach this stage, becoming red giants as their outer layers expand. More massive stars continue the process, fusing carbon into oxygen, oxygen into neon, neon into magnesium, and so on, building heavier and heavier elements in their cores. Each stage of fusion requires higher temperatures because heavier nuclei have more protons, creating stronger electromagnetic repulsion that must be overcome. The star's core becomes layered like an onion, with different elements fusing in different shells. Iron is the endpoint. Fusing nuclei lighter than iron releases energy, but fusing iron requires an input of energy. When a massive star builds an iron core, fusion can no longer support the star. Gravity wins, the core collapses, and the result is a supernova, an explosion so powerful it can briefly outshine an entire galaxy. Stars are also the universe's alchemists. The first stars contained only hydrogen and helium, the elements created in the Big Bang. Through fusion, they forged heavier elements: carbon, nitrogen, oxygen, silicon, iron. When those stars died, they scattered these elements into space. Later generations of stars incorporated this enriched material, allowing even heavier elements to form. Supernovae and neutron star collisions create the heaviest elements: gold, uranium, platinum, through rapid neutron capture. Every atom in your body, heavier than hydrogen, was created in a star. You are, quite literally, made of stardust. The sun's power output, 3.8 times 10 to the 26th watts, is almost incomprehensible. To match it, you would need billions upon billions of large power plants. And the sun is average. Some stars are thousands of times more luminous, radiating energy at rates that dwarf our sun. Others are dimmer, barely visible even from nearby. But all of them, from the faintest red dwarf to the most brilliant blue supergiant, run on fusion. It is the universal power source, the engine that lights the cosmos. Humanity dreams of replicating stellar fusion on Earth. Fusion power would provide nearly limitless clean energy, using hydrogen from water as fuel and producing helium as waste. The challenge is enormous confining plasma at temperatures of tens of millions of degrees, maintaining the reaction, extracting more energy than is put in. Experimental reactors use powerful magnetic fields or intense laser pulses to achieve these conditions, inching closer to sustained fusion. If successful, it would represent harnessing the power of stars, bringing the engine of the cosmos down to human scale. Stars are more than light sources. They are the architects of chemistry, the forges where elements are made. They regulate galaxies through their radiation and stellar winds. They explode, enriching the interstellar medium. From birth to death, stars shape the universe, transforming hydrogen into complexity, releasing energy that propagates across space and time. They are fusion engines, burning steadily for eons, each one a testament to the power locked in atomic nuclei, waiting to be released. For most of their lives, stars exist in balance, gravity pulling inward, fusion pushing outward, the two forces in delicate equilibrium. This balance can last for millions, billions, even trillions of years, but it cannot last forever. Star exhausts its nuclear fuel. When fusion can no longer generate enough pressure to resist gravity's pull, the balance breaks. For the most massive stars, this breaking point leads to one of the most powerful events in the universe, releasing more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. Supernovae come in different types, but the most common and most spectacular are core collapse supernovae, the deaths of massive stars. A star must be at least 8 times the mass of the sun to end this way. These giants burn through their hydrogen quickly, then helium, then carbon, oxygen, neon, and silicon, building heavier elements in concentric shells around their cores. Each stage of fusion lasts a shorter time than the last, because heavier elements yield less energy per fusion reaction. A star might burn hydrogen for millions of years, helium for hundreds of thousands, carbon for centuries, and silicon for just days. The final product of this fusion sequence is iron. Iron is special. Nuclei lighter than iron release energy when fused together. Nuclei heavier than iron require energy input to fuse. This means that when a star builds an iron core, it has reached a dead end. No further fusion is possible that would generate outward pressure. The iron core grows, accumulating mass, but contributing nothing to the star's support. Gravity, patient and relentless, waits. When the iron core reaches a critical mass about 1.4 times the mass of the Sun, a limit called the Chandrasekhar limit, it can no longer support itself even against electron degeneracy pressure. In less than a second, the core collapses. Electrons and protons are crushed together, forming neutrons and releasing vast numbers of neutrinos. The core, with more mass than the Sun, shrinks to a sphere perhaps 20 kilometers across. This collapse is one of the most extreme events in nature, compressing matter to densities where a teaspoon would weigh as much as a mountain. The collapse is so rapid that the outer layers of the star, still falling inward, don't have time to react. They crash into the now solid neutron core and rebound. The shock wave from this rebound, combined with the energy carried by neutrinos escaping from the core, blasts the outer layers into space at speeds of tens of thousands of kilometers per second. This is the supernova, a catastrophic explosion that tears the star apart, scattering its enriched material across light years of space. The energy released is staggering. A typical core collapse supernova releases about 10 to the 46 joules of energy, most of it in the form of neutrinos that escape almost immediately, carrying information about the core's collapse to the universe. The remaining energy, about 1% of the total, but still enormous, goes into the kinetic energy of the ejected material and the electromagnetic radiation we see as light. For weeks, the supernova can shine as brightly as billions of stars combined, visible across millions of light years. This brilliance is a turning point in multiple senses. It marks the death of a star, the end of a fusion engine that may have burned for millions of years, but it is also a beginning. The explosion disperses heavy elements, carbon, oxygen, iron, gold, into the interstellar medium. These elements, forged in the star's core and in the explosion itself, become part of the raw material for future generations of stars and planets. Without supernovae, the universe would contain only hydrogen and helium. There would be no rocky planets, no water, no organic chemistry, no life. Supernovae are both destruction and creation, violent ends that seed new beginnings. There is also another type of supernova, called type Ia, which follows a different path but achieves comparable brilliance. These occur in binary star systems, where a white dwarf, a dense remnant of a lower mass star, accretes material from a companion. When the white dwarf's mass reaches the Chandrasekhar limit, it undergoes runaway thermonuclear fusion, exploding completely. No neutron star or black hole is left behind. The entire star is obliterated. Because these explosions always happen at roughly the same mass, they have remarkably consistent peak brightness, making them valuable as standard candles for measuring cosmic distances. It was through studying Type Ia supernovae that astronomers discovered the universe's expansion is accelerating, driven by dark energy. By comparing the expected brightness of distant supernovae to their observed brightness, scientists realized they were farther away than predicted, indicating that space itself has been stretching faster over time. This discovery reshaped cosmology, revealing that a mysterious component dominates the universe's energy budget. Supernovae, in their dying light, became probes of the cosmos itself. The remnants of supernovae are extraordinary in their own right. If the collapsing core has less than about 3 times the Sun's mass, it stabilizes as a neutron star, an object so dense that atomic nuclei touch, held up only by neutron degeneracy pressure. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like lighthouse beams. These are pulsars. Others have magnetic fields trillions of times stronger than Earth's, becoming magnetars that can unleash bursts of energy powerful enough to affect instruments across light years. If the core is more massive still, not even neutron degeneracy pressure can stop the collapse. Gravity overwhelms all resistance, and the core collapses into a black hole, a region where space-time curves so steeply that nothing, not even light, can escape. Black holes are among the most extreme objects in the universe, and many are born in the violent cores of supernovae. The turning point of a supernova is thus also the birth of these exotic remnants, each one a laboratory for physics at its limits. Supernovae have been observed and recorded throughout human history. Ancient astronomers noted guest stars appearing suddenly in the sky, shining brightly for weeks or months before fading. The supernova of 1054, observed by Chinese astronomers, created the Crab Nebula, an expanding cloud of gas still visible today. In 1572 and 1604, supernovae visible to the naked eye appeared in our galaxy, observed by Tycho Brahe and Johannes Kepler respectively. These events challenged the Aristotelian view that the heavens were unchanging, contributing to the scientific revolution. Modern telescopes detect supernovae in distant galaxies regularly, sometimes several per day across the observable universe. Each one is studied intensely, its light curve, spectrum, and remnants providing data about stellar evolution, nucleosynthesis, and cosmic expansion. Neutrino detectors have even captured the neutrino burst from a nearby supernova SN 1987A in the Large Magellanic Cloud, providing direct evidence of core collapse and confirming theoretical predictions. The violence of supernovae is a reminder that the universe is not static or gentle. Stars do not simply fade away. The most massive among them end in catastrophic explosions, releasing in seconds the energy the sun will produce over billions of years. This violent brilliance is essential. It enriches the cosmos, creates neutron stars and black holes, and drives the evolution of galaxies. The turning point of a supernova is where stellar death becomes cosmic creation, where destruction fuels the ongoing story of the universe. There are places in the universe where gravity has become so strong that it has fundamentally altered the nature of space and time. These are not simply regions where things fall faster or orbits tighten. They are places where the fabric of reality itself is warped beyond recognition, where the usual rules break down, where even light travelling at the cosmic speed limit cannot escape. These places are black holes, and they represent gravity taken to its ultimate extreme, a consequence of matter compressed past every threshold, every limit, every point of resistance. Black holes form when gravity overwhelms all other forces. In the death of a massive star, after the supernova explosion scatters the outer layers, if the remaining core has more than about 3 times the mass of the Sun, nothing can stop its collapse. Electron degeneracy pressure, which supports white dwarfs, fails under the weight. Neutron degeneracy pressure, which supports neutron stars, also fails. The core collapses inward, shrinking past the size of a city, past the size of a mountain, past every scale, until it becomes a point of infinite density, a singularity surrounded by a region from which nothing can escape. The boundary of this region is called the event horizon. It's not a physical surface you could touch, but a mathematical boundary in space-time. Cross the event horizon moving inward, and you can never return. All paths lead further in. Time and space exchange roles. In a sense, just as you cannot avoid moving forward in time outside a black hole, inside the horizon, you cannot avoid moving toward the singularity. The event horizon marks the point of no return, the threshold where escape velocity equals the speed of light and nothing, not even light itself, moves fast enough to climb back out. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of the Sun, the event horizon would have a radius of about 3 kilometers. For a supermassive black hole with 1 billion solar masses like those found at the centers of large galaxies, the event horizon stretches to billions of kilometers, larger than our solar system. Yet all that mass, no matter how much, is concentrated at the central singularity, a point of zero size and infinite density where Einstein's equations break down and our understanding fails. Black holes are invisible by definition. They emit no light, but they reveal themselves through their effects on nearby matter. Gas falling toward a black hole forms an accretion disk, a swirling spiral of material heated to millions of degrees by friction and compression. This superheated gas radiates intensely across the electromagnetic spectrum, from radio waves to X-rays. Some of the brightest objects in the universe are powered by black holes consuming matter. Their accretion disks outshining entire galaxies, even though the black hole itself remains dark. Some black holes produce jets, narrow beams of particles and radiation launched from near the event horizon at nearly the speed of light. These jets can extend for thousands or even millions of light years, piercing through galaxies and illuminating vast regions of space. The exact mechanism isn't fully understood, but it involves the black hole's rotation and powerful magnetic fields threading through the accretion disk. The energy released by matter falling into a black hole can be converted with extraordinary efficiency into these jets, making them some of the most powerful phenomena in the cosmos. There are different types of black holes classified by mass. Stellar mass black holes, formed from collapsing stars, typically range from a few to a few dozen times the Sun's mass. Intermediate mass black holes, if they exist, would fill the gap between stellar and supermassive. Supermassive black holes, millions to billions of times the Sun's mass, lurk at the centers of most large galaxies, including our own Milky Way. The black hole at the center of our galaxy, Sagittarius A*, has about 4 million solar masses. Other galaxies harbor even larger monsters. How supermassive black holes form is still debated. They may have grown from stellar mass black holes that merged and accreted matter over billions of years. They may have formed from the direct collapse of massive gas clouds in the early universe. They may have originated as seeds from the very first generation of stars. Whatever their origin, these giants play a crucial role in galactic evolution. Their gravity influences the motions of stars near galactic centers, and their activity through radiation and jets can regulate star formation across entire galaxies. Black holes also feature in one of the most dramatic confirmations of Einstein's general relativity, the detection of gravitational waves. When two black holes spiral into each other and merge, they send ripples through spacetime itself, waves that propagate outward at the speed of light. These gravitational waves were first detected in 2015 by the LIGO Observatory, opening a new window on the universe. The collision that produced the signal released more power in gravitational waves for a fraction of a second than all the stars in the observable universe combined were radiating as light. This is power of a different kind, not electromagnetic energy, but spacetime itself vibrating, carrying energy away from a cosmic cataclysm. Near a black hole, time itself behaves strangely. Clocks run slower in stronger gravitational fields, an effect called gravitational time dilation. An observer watching someone fall toward a black hole would see them moving slower and slower as they approach the event horizon, their image freezing and fading as photons struggle to escape the deepening gravity well. For the falling observer, time feels normal, but they cross the horizon in finite time and continue falling toward the singularity. The difference in perspectives, one seeing an eternal approach, the other a swift plunge, illustrates how deeply gravity affects time. Inside the event horizon lies the singularity, where all the black hole's mass is concentrated. Our current theories predict infinite density and curvature at this point, but infinities in physics usually signal that the theory has reached its limits. Quantum effects, which general relativity doesn't account for, must become important at such extreme scales. A complete theory of quantum gravity, still undeveloped, would be needed to describe what truly exists at the center of a black hole. It might not be a point, but a region smoothed by quantum mechanics, or something even stranger. Black holes also raise profound questions about information. Quantum mechanics insists that information cannot be destroyed, yet general relativity suggests that anything falling into a black hole is lost forever, its information erased beyond the event horizon. This tension is called the information paradox. Stephen Hawking proposed that black holes emit radiation due to quantum effects near the horizon, now called Hawking radiation. This radiation causes black holes to slowly evaporate over immense timescales, potentially releasing information. But how information escapes from a region where escape seems impossible remains an open question, hinting at deeper connections between gravity, quantum mechanics, and the nature of reality. For stellar mass black holes, Hawking radiation is negligible. They would take far longer than the current age of the universe to evaporate. For supermassive black holes, the timescales are even more extreme. But for hypothetical tiny black holes, if they exist, evaporation could be rapid, releasing energy in a final burst. Whether such micro-black holes formed in the early universe, or could be created in high-energy collisions, is speculative, but explored in theoretical physics. Black holes are consequences of massive stars dying, of gravity winning, of matter collapsing past every resistance. They are the universe's ultimate demonstration of gravitational power. Regions where space-time is bent into configurations so extreme that they challenge our understanding and stretch our theories to breaking. They swallow matter and light, yet paradoxically power some of the brightest phenomena through the energy released just outside their grasp. They are dark hearts in a luminous cosmos, silent yet influential, mysterious yet increasingly understood. In them, we see gravity not as a gentle pull but as an overwhelming force capable of transforming reality itself. If black holes represent gravity's ultimate victory, neutron stars are gravity's last stand before total collapse. They are what remains when a massive star explodes in a supernova, but the core isn't quite heavy enough to form a black hole. Instead, the core is compressed into one of the densest forms of matter known to exist. A ball of neutrons packed so tightly that a teaspoon of the material would weigh about 1 billion tons. Neutron stars are laboratories of extreme physics, places where matter exists in states impossible to recreate on Earth, where magnetic fields reach strengths trillions of times greater than anything we know, and where the boundaries of our understanding are constantly tested. The formation of a neutron star happens in the violent core of a dying massive star. As the iron core collapses, electrons and protons are forced together by immense pressure, combining to form neutrons and releasing neutrinos in the process. This flood of neutrinos carries away most of the energy from the collapse, but what remains is a core of nearly pure neutrons, supported against further collapse by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same quantum state. This pressure is incredibly strong, but it has limits. If the core's mass exceeds about 3 times the Sun's mass, even neutron degeneracy pressure fails, and a black hole forms instead. A typical neutron star packs about 1.4 times the Sun's mass into a sphere only about 20 kilometers in diameter, roughly the size of a city. This means neutron stars are extraordinarily dense, with matter compressed to nuclear densities and beyond. To put this in perspective, the entire human population could fit into a volume the size of a sugar cube if compressed to neutron star density. The surface gravity is about 200 billion times stronger than Earth's. Escape velocity from the surface is approximately half the speed of light. If you could somehow stand on a neutron star's surface, you would be crushed instantly, flattened to a layer atoms thick. The interior structure of neutron stars is layered and exotic. The outermost layer is a thin crust of iron nuclei and electrons, similar to ordinary matter, but compressed to densities millions of times greater than terrestrial materials. Below this lies a region where neutrons begin to drip out of nuclei, forming a neutron-rich fluid. Deeper still, the matter becomes a superfluid of neutrons, a state where quantum effects allow frictionless flow. At the very center, conditions may be extreme enough to create quark matter, a soup of free quarks and gluons no longer bound into neutrons. Some theories even propose that the cores of the most massive neutron stars might contain strange quark matter or other exotic states we've barely begun to imagine. Neutron stars rotate, and many rotate extraordinarily fast. When a massive star collapses, conservation of angular momentum causes the core to spin more rapidly, just as a figure skater spins faster when pulling their arms inward. Some neutron stars, called pulsars, rotate hundreds of times per second. The fastest known pulsar spins at 716 rotations per second, a ball of matter more massive than the Sun, 20 kilometers across, spinning so fast that its equator moves at a significant fraction of the speed of light. The precision of these rotations rivals atomic clocks, making pulsars among the most accurate timekeepers in the universe. Pulsars emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space like a lighthouse. If Earth happens to lie in the path of the beam, we detect regular pulses of radio waves, X-rays or gamma rays, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, initially mistaken for an artificial signal due to its remarkable regularity. Since then, thousands have been found, each one providing insights into matter under extreme conditions and tests of general relativity in strong gravitational fields. The magnetic fields of neutron stars are among the strongest in the universe. During collapse, the star's original magnetic field is compressed, along with everything else, amplifying its strength. Typical neutron stars have fields about 1 trillion times stronger than Earth's. But some neutron stars, called magnetars, have fields 1,000 times stronger, still quadrillions of times Earth's field. These are the most powerful magnets known, strong enough that the magnetic field itself can distort the shapes of atoms. Near a magnetar, quantum effects induced by the magnetic field would make empty space birefringent, causing light to split into polarized beams as if passing through a crystal. Magnetars occasionally produce starquakes, sudden cracks in their solid crusts caused by stress from the shifting magnetic field. These events release enormous bursts of energy, mostly in the form of gamma rays and X-rays. In December 2004, a magnetar about 50,000 light-years away produced a flare so intense that it affected Earth's ionosphere. Despite the vast distance, for 1/10 of a second, that single flare released more energy than the Sun emits in 200,000 years. Such events demonstrate the sheer power concentrated in these compact objects. Neutron stars also participate in some of the most energetic collisions in the universe. When two neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves. Eventually, they merge in a catastrophic collision. These mergers produce gravitational wave signals detectable by observatories like LIGO and Virgo. They also produce electromagnetic radiation across the spectrum, from gamma rays to radio waves, a kilonova, brighter than a typical supernova, but not as bright as the most massive stellar explosions. The first neutron-star merger detected with both gravitational waves and light occurred in August 2017. The event confirmed theoretical predictions and revealed that such mergers are likely the primary sources of heavy elements like gold, platinum, and uranium. The extreme conditions, temperatures of billions of degrees, densities exceeding nuclear matter, and intense neutron fluxes allow rapid neutron capture processes that create these elements. In a very real sense, the gold in jewelry and electronics was forged in neutron-star collisions billions of years ago, scattered into space, and eventually incorporated into the cloud that formed our solar system. Neutron stars serve as natural laboratories for physics that cannot be studied any other way. The equations of state for matter, the relationships between pressure, density, and temperature, are tested at extremes far beyond anything achievable in particle accelerators. Observations of neutron star masses and radii constrain these equations, helping physicists understand the strong nuclear force and the behavior of matter at supranuclear densities. Neutron stars also provide tests of general relativity in strong gravitational fields, confirming predictions about spacetime curvature, frame dragging, and gravitational redshift. Some neutron stars are found in binary systems with ordinary stars. The neutron star's intense gravity pulls material from its companion, forming an accretion disk. As this material spirals inward, it heats up and emits X-rays, making these systems bright X-ray sources. If enough material accumulates on the neutron star's surface, it can ignite in a thermonuclear explosion, producing an X-ray burst, a brief, intense flash that can momentarily outshine thousands of suns. The impact of neutron stars extends beyond their individual characteristics. They populate galaxies as remnants of massive star evolution, contributing to the chemical enrichment of the interstellar medium. They serve as cosmic clocks and tests of fundamental physics. They produce some of the most extreme magnetic fields, densities, and energies observed anywhere. And they remind us that matter, when compressed beyond ordinary limits, doesn't simply vanish into black holes, but can exist in forms both strange and stable, balanced on the edge of gravitational collapse. Neutron stars are compressed power mass concentrated to the limits of what quantum mechanics allows. Energy stored in rotation, magnetic fields, and gravitational potential. They are small by cosmic standards, yet each one carries the mass of the Sun and the imprint of some of the most violent events in the universe. Understanding them pushes the boundaries of physics, revealing what happens when matter is squeezed past every familiar form into states so extreme they challenge our imagination and our theories alike. When astronomers measure the mass of a galaxy by observing the motion of its stars and gas, they encounter a profound mystery. The stars orbit the galactic center far too quickly for the visible matter alone to hold them in place. According to Newton's laws and Einstein's refinements, objects farther from a gravitational center should move more slowly, just as planets farther from the Sun orbit more gradually. Yet in galaxy after galaxy, the rotation curves stay flat. Stars at the edge move nearly as fast as those near the center. The only explanation is that galaxies contain far more mass than we can see, an invisible component that provides the extra gravitational pull needed to keep everything bound together. This invisible component is what scientists call dark matter. It doesn't emit, absorb, or reflect light. It doesn't interact through electromagnetic forces at all. It makes its presence known solely through gravity, through the way it bends light from distant sources, through the motions of galaxies in clusters, through the large-scale structure of the universe itself. Dark matter is invisible, yet it outweighs all the stars, planets, gas, and dust in the universe combined. Roughly 85% of the matter in the cosmos is dark, leaving ordinary matter, the stuff we're made of, the stuff we can see, as just a small fraction of the total. The evidence for dark matter comes from multiple, independent observations. Vera Rubin's work on galaxy rotation, curves in the 1,970 seconds, provided some of the first clear evidence. Galaxy clusters, like the Coma cluster studied earlier by Fritz Zwicky, move in ways that require far more mass than is visible. Gravitational lensing, the bending of light by massive objects, reveals the presence of matter where nothing luminous exists. The cosmic microwave background, the afterglow of the Big Bang, contains subtle patterns that can only be explained if dark matter was present in the early universe, providing gravitational seeds for structure formation. One of the most dramatic pieces of evidence comes from the Bullet cluster, where two galaxy clusters collided. The hot gas in each cluster, visible in X-rays, slowed and interacted during the collision. But gravitational lensing shows that the majority of the mass passed right through, separating from the gas. This indicates that most of the matter is dark, collisionless, interacting only through gravity, while ordinary matter interacts electromagnetically and slows down. The Bullet cluster provides a clear visual separation between dark and ordinary matter. What is dark matter made of? Nobody knows for certain. It's one of the biggest open questions in physics. The leading candidates are particles that have mass, but don't interact electromagnetically. Weakly interacting massive particles, or WIMPs, are one possibility. These hypothetical particles would interact through gravity and the weak nuclear force, but not through electromagnetism or the strong force. They would pass through ordinary matter almost undetected, rarely colliding with atoms. Despite extensive searches using sensitive detectors deep underground, shielded from cosmic rays and background radiation, WIMPs have not been conclusively detected. Another candidate is the axion, a much lighter particle predicted by certain extensions of particle physics. Axions would be produced in enormous numbers, but interact even more weakly than WIMPs. Experiments are underway to detect them through their subtle interactions with magnetic fields. Sterile neutrinos, hypothetical cousins of ordinary neutrinos, that interact only through gravity are another possibility. Each candidate has different properties and would require different detection methods. The search continues, driven by the certainty that dark matter exists even though we don't yet know what it is. Dark matter played a crucial role in the formation of structure in the universe. After the Big Bang, the cosmos was nearly uniform, with only tiny density fluctuations. Ordinary matter was too hot initially, moving too fast for gravity to gather it into clumps. But dark matter, which doesn't interact with radiation, could begin collapsing under its own gravity immediately. These collapsing dark matter halos provided gravitational wells into which ordinary matter could later fall, cooling and forming galaxies. Without dark matter, galaxies wouldn't have formed when they did, and the universe might look very different today. Computer simulations of cosmic structure formation include dark matter and reproduce the large-scale patterns we observe. The cosmic web of filaments and voids, the distribution of galaxies, the clustering on different scales. These simulations start with initial conditions from the early universe and evolve them forward using gravity. When dark matter is included, the results match observations remarkably well. When it's left out, the simulations fail to produce the structures we see. This computational evidence, combined with observational data, makes a compelling case for dark matter's existence. Every galaxy, including our own Milky Way, is embedded in a dark matter halo. This halo extends far beyond the visible disk, possibly hundreds of thousands of light-years into space. As the solar system orbits the galactic center, it moves through this halo. Dark matter particles would be passing through Earth, through your body, constantly billions of them every second, but they interact so weakly that they pass through without leaving a trace. You are, at this moment, immersed in dark matter, surrounded by its invisible weight, yet completely unaware of it at a sensory level. The human element here is perspective. We evolved to sense electromagnetic radiation light and to interact with matter through electromagnetic forces. Our eyes detect photons. Our hands feel electromagnetic repulsion between atoms. Our entire experience of the material world is mediated by electromagnetism. Dark matter exists outside this sensory experience. It's a reminder that reality extends beyond what we can directly perceive, that the universe contains components we can only infer through their effects, through careful observation and measurement, through the application of reason and mathematics to phenomena we cannot touch or see. Dark matter also shapes the fate of galaxies. The Milky Way and Andromeda are on a collision course, drawn together by mutual gravitational attraction. Their dark matter halos will merge long before their stellar populations interact. The combined dark matter will create a new gravitational well, shaping the eventual outcome of the collision. On the largest scales, dark matter determines how galaxy clusters evolve, how voids form, how the cosmic web is structured. It is the invisible scaffolding on which the visible universe is built. There are alternative theories. Some physicists have proposed modifying the laws of gravity rather than invoking dark matter theories like modified Newtonian dynamics, MOD, or tensor vector scalar gravity. These alternatives attempt to explain observations without requiring new particles. While they can explain some observations, they struggle with others, particularly the bullet cluster and the cosmic microwave background. Dark matter remains the leading explanation because it fits the widest range of data with the fewest adjustments to established physics. Solving the mystery of dark matter would be transformative. Discovering the particle would open new physics beyond the standard model, potentially connecting to questions about the early universe, symmetry, and the fundamental forces. It might reveal connections between particle physics and cosmology, between the very small and the very large. Understanding dark matter could reshape our view of reality as profoundly as quantum mechanics and relativity did in the 20th century. For now, dark matter remains invisible, weight felt but not seen, inferred but not isolated, dominating the mass budget of the universe, yet eluding direct detection. It reminds us that the cosmos has depths we're only beginning to explore. that power in the universe is not always visible or obvious, that the most influential components can be the ones hidden from view. In dark matter, we see the universe's capacity for mystery, its refusal to yield all its secrets easily, and the human capacity for persistence in the face of the unknown. If dark matter is the invisible scaffolding that holds galaxies together, dark energy is the mysterious force pushing the entire universe apart. In the late 1990 seconds, two teams of astronomers studying distant supernovae made a discovery that shocked the scientific community. The expansion of the universe is not slowing down, as gravity would suggest, but speeding up. Galaxies are accelerating away from each other, driven by something that permeates all of space. Something that doesn't pull like gravity but pushes, acting as a kind of cosmic anti-gravity. This something is called dark energy, and it makes up roughly 70% of the total energy content of the universe. The discovery came from observations of Type Ia supernovae, which serve as standard candles because they have consistent peak brightness. By comparing their known luminosity to their observed brightness, astronomers can calculate their distances. By measuring the redshift of their light, how much the expansion of space has stretched the wavelengths, astronomers can determine how fast those galaxies are receding. The expectation was that distant galaxies, seen as they were billions of years ago, would be receding more slowly than predicted if gravity had been gradually slowing the expansion. Instead, the data showed the opposite. Distant supernovae were fainter than expected, indicating they were farther away than models predicted. The only way to explain this was if the expansion rate had increased over time. Something was accelerating the expansion, counteracting gravity's pull. The discovery was so unexpected, so contrary to intuition, that both teams checked their data multiple times before publishing. But the results held. In 2011, the leaders of these teams were awarded the Nobel Prize in Physics for revealing that the universe's expansion is accelerating. What is dark energy? The simplest explanation is the cosmological constant, a term Einstein originally introduced into his equations of general relativity and later discarded. The cosmological constant represents a form of energy inherent in space itself, vacuum energy, that doesn't dilute as the universe expands. Instead, as space grows, more vacuum comes into existence, and with it, more energy. This creates a repulsive effect that increases as the universe gets larger, pushing galaxies apart at ever-increasing rates. If dark energy is indeed a cosmological constant, it would mean that empty space has a fixed energy density, the same everywhere and at all times. In quantum field theory, the vacuum is not truly empty but filled with fluctuating fields. Calculating the vacuum energy from first principles yields a value enormously larger by a factor of about 10 to the 120 than what's observed. This mismatch, sometimes called the cosmological constant problem or the vacuum catastrophe, is one of the most severe discrepancies between theory and observation in all of physics. Why the observed value is so small, yet not zero, remains deeply mysterious. Another possibility is that dark energy is not constant but dynamic, varying over time or space. Models with such fields go by names like quintessence, referring to a hypothetical fifth fundamental force or component. These models predict that the strength of dark energy might change as the universe evolves, which would affect the expansion rate differently at different epochs. Distinguishing between a true cosmological constant and a dynamic field requires precise measurements of the universe's expansion history, something cosmologists are actively pursuing through surveys of galaxies, supernovae, and the cosmic microwave background. Dark energy's effects are only noticeable at the largest scales. Within galaxies or even galaxy clusters, gravity is strong enough that dark energy's repulsive effect is negligible. But across hundreds of millions or billions of light years, dark energy dominates. It overwhelms gravity, driving the accelerated expansion that will shape the universe's ultimate fate. In the distant future, as dark energy continues to push space apart, galaxies beyond our local group will recede beyond the cosmic horizon, becoming forever unreachable. The observable universe will shrink, in a sense, as distant regions accelerate away faster than light can travel through the expanding space between us. The competition between dark energy and gravity determines the cosmos's destiny. If gravity was stronger or dark energy weaker, the expansion might eventually reverse, pulling everything back into a big crunch. If dark energy strengthens over time, it could eventually overwhelm even the forces holding galaxies, solar systems, and atoms together, tearing the universe apart in a big rip. Current evidence suggests a more gradual fate, continued expansion and cooling, with structures surviving locally while the universe becomes increasingly empty and dark on large scales. A scenario sometimes called the Big Freeze or heat death. Dark energy also connects to fundamental Big Freeze. Questions about the nature of spacetime and quantum mechanics. If it's vacuum energy, then empty space has intrinsic properties. It weighs something. It exerts pressure. It influences the curvature of spacetime. This challenges our intuitions about what nothing means. The vacuum becomes an active participant in cosmic evolution, not just a passive stage on which events unfold. Understanding dark energy might require reconciling quantum field theory with general relativity, a unification that has eluded physicists for decades. Some cosmologists have explored the idea that we might live in a multiverse, where different regions of space or different bubble universes have different amounts of dark energy. In this view, our universe happens to have a value compatible with galaxy formation and life, while other regions might have values too large or too small to allow structures to form. This anthropic reasoning is controversial. It shifts the question from why does dark energy have this value to why do we find ourselves in a universe where it has this value? But it reflects the deep puzzlement the cosmological constant problem inspires. Observational campaigns continue to refine our understanding of dark energy. Large sky surveys map millions of galaxies, measuring their distances and redshifts to trace the expansion history. Studies of galaxy clustering, gravitational lensing, and the cosmic microwave background all provide constraints. Future space telescopes and ground-based observatories will push these measurements to higher precision, testing whether dark energy is truly constant or evolving, and whether general relativity accurately describes gravity on cosmic scales. The opposition between dark energy and gravity is also philosophical. Gravity is attractive, pulling things together, creating structure. Dark energy is repulsive, pushing things apart, fostering emptiness. Gravity shapes the universe on local and intermediate scales, building galaxies and clusters. Dark energy shapes it on the larger scales, determining its expansion and ultimate fate. The two forces are locked in a cosmic tug-of-war, and dark energy is winning. As the universe ages, its influence grows, and gravity's ability to gather matter into new structures weakens. There's also a poetic irony. Dark energy is the dominant component of the universe, yet it's the least understood. It exerts more influence than all the matter combined, yet we don't know what it is. It determines the cosmos's future, yet it remains one of the greatest mysteries. Power, in this case, is not visible or tangible, but pervasive and inexorable. A gentle but relentless pressure that will shape the universe for trillions of years to come. In dark energy, we see that the most powerful things need not announce themselves loudly. They can work quietly, invisibly, altering everything simply by existing. There is a boundary in physics, a frontier where our current theories begin to falter and the rules we rely on cease to apply. This boundary is not a place in space or a moment in time, but a scale, the Planck scale, named after the physicist Max Planck, who first recognized its significance. At this scale, quantum mechanics and general relativity, the two pillars of modern physics, collide. The quantum world of particles and the geometric world of curved spacetime cannot be reconciled with our current understanding. The Planck scale represents the limits of what we can describe, the edge of knowledge where the universe's deepest secrets may lie hidden. The Planck scale is defined by combining the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. From these, we can derive the Planck length, approximately 1.6 times 10 to the negative 35 meters, unimaginably small, far tinier than an atom or even a proton. At this scale, the quantum foam of space-time fluctuations might become significant, and the smooth fabric of space-time described by general relativity might break down into something discrete, granular, or fundamentally different. Similarly, the Planck time is about 5.4 times 10 to the negative 44 seconds, the time it would take light to cross a Planck length. This is the shortest interval of time that has physical meaning in our current theories. The Planck energy, about 10 to the 19th giga-electron-volts, is the energy scale where quantum gravitational effects become important. To put this in perspective, the Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 to the 4 giga-electron-volts, 15 orders of magnitude below the Planck energy. We cannot probe the Planck scale experimentally with current or foreseeable technology. Why does the Planck scale matter for understanding power in the universe? Because it represents the ultimate limits of energy density, the maximum concentration of power that nature allows before our understanding fails. Black hole singularities, the first moments of the Big Bang, and perhaps even the vacuum itself on the smallest scales, all involve physics at or near the Planck regime. To truly understand the most powerful phenomena in the powerful, fair universe, we would need a theory that works at the Planck scale, a theory of quantum gravity. General relativity describes gravity beautifully on large scales, bending space-time around massive objects, predicting black holes and gravitational waves. But it treats space-time as smooth and continuous. Quantum mechanics, equally successful, describes particles and forces at tiny scales, treating them as discrete, probabilistic entities. At the Planck scale, both descriptions are necessary. Space-time itself must be quantized, subject to uncertainty and fluctuation. But combining the two theories has proven extraordinarily difficult. In general relativity, singularities, points of infinite density, appear in the solutions for black holes in the Big Bang. These infinities signal that the theory has broken down, that something is missing. Quantum mechanics abhors infinities, smoothing them out through uncertainty principles and quantum fluctuations. A quantum theory of gravity should eliminate the singularities, replacing them with finite structures described by new physics. What lies at the center of a black hole? What happened at the very first instant of the Big Bang? These questions require understanding physics at the Planck scale. String theory is one attempt to bridge this gap. It proposes that the fundamental constituents of the universe are not point particles, but tiny, vibrating strings, with lengths on the order of the Planck length. Different vibrational modes of these strings correspond to different particles, electrons, photons, quarks, and even gravitons. The hypothetical carriers of gravity. String theory naturally incorporates gravity, potentially unifying it with the other forces. It also requires extra spatial dimensions beyond the three we experience. Dimensions that might be compactified or hidden at scales near the Planck length. Loop quantum gravity takes a different approach, focusing on quantizing spacetime itself. It suggests that space is not continuous, but made of discrete, indivisible units, loops woven into a network that gives rise to geometry. At the Planck scale, spacetime would have a granular structure, like pixels on a screen. This quantization could eliminate singularities, replacing the infinite densities of black holes and the Big Bang with finite, though extraordinarily large, values. Both string theory and loop quantum gravity remain speculative, with no experimental evidence yet confirming or ruling them out. The Planck scale also sets a limit on black hole formation. If you try to concentrate enough energy into a region smaller than the Planck length, quantum effects would prevent a classical singularity from forming. Instead, you might create a Planck-scale black hole, an object with a mass about 22 micrograms, tiny by everyday standards but enormous by particle physics standards. Such a black hole would evaporate almost instantly through Hawking radiation, releasing its mass energy in a burst lasting about 10 to the negative 44 seconds. Whether such objects can exist or have ever existed is unknown, but they illustrate the interplay between quantum mechanics and gravity at extreme scales. The early universe provides the closest natural laboratory for Planck-scale physics. In the first 10 to the negative 43 seconds after the Big Bang, the Planck epoch, the universe was so hot and dense that quantum gravitational effects dominated. Our current theories cannot describe this era. What came before, if before even makes sense? Did time itself emerge from a timeless quantum state? Was there a singularity? Or did quantum effects smooth the beginning into a bounce from a previous contracting phase? These questions remain unanswered, awaiting a theory that works at the Planck scale. The Planck scale also hints at fundamental limits on measurement and information. The Heisenberg uncertainty principle prevents us from knowing both position and momentum precisely. At the Planck scale, attempting to measure a position more precisely would require so much energy concentrated in such a small region that it would create a black hole, obscuring the very thing you're trying to measure. In this sense, the Planck scale is not just a practical limit, but a fundamental one written into the structure of reality itself. Energy density at the Planck scale is almost beyond comprehension. The Planck energy density is about 10 to the 113 joules per cubic meter, a number so large that if you tried to create it in a laboratory-sized volume, the energy would collapse into a black hole. This is the maximum energy density that can exist in a region of space before gravity dominates and structure collapses. It represents the ultimate power density, the frontier beyond which our concepts of space, time, and energy break down. Understanding the Planck scale also has implications for unification. At low energies, the four fundamental forces appear, distinct. As energy increases, forces begin to merge the electromagnetic, and weak forces unify into the electro-weak interaction at energies achieved in particle accelerators. At higher energies, the strong force may unify with the electro-weak. At the Planck energy, all forces, including gravity, might merge into a single, unified interaction. If true, the Planck scale represents not just a boundary, but a simplification, a return to the fundamental unity that existed in the first moments after the Big Bang. The awakening, represented by the Planck scale, is both humbling and inspiring. It shows us the limits of our current knowledge, the scales where our best theories falter, but it also points toward deeper truths, toward a more complete understanding of reality that unifies quantum mechanics and gravity, that explains singularities in the beginning of time, that reveals the ultimate nature of spacetime and energy. We cannot yet reach the Planck scale experimentally, but we can explore it theoretically, mathematically, and perhaps one day observationally through subtle imprints left on the cosmic microwave background or gravitational waves from the early universe. The Planck scale is the frontier where power becomes not just a measure of energy transfer, but a question about the nature of existence itself. It is where the universe's most powerful moments, its birth, the cause of black holes must be understood. And it is where the future of physics lies, waiting for the insights that will awaken us to the deepest workings of the cosmos. Empty space, we are told, is a vacuum, a region devoid of matter, particles, and substance. Intuitively, this should mean that a perfect vacuum contains nothing at all, that it is the absence of everything. But quantum mechanics reveals a profoundly different picture. Even in the emptiest regions of space, far from any stars or galaxies, the vacuum is not truly empty. It is alive with activity, filled with fields that fluctuate, particles that appear and vanish in fractions of a second, and energy that permeates every cubic centimeter of existence. This revelation that the vacuum has structure and energy reshapes our understanding of what it means for space to be empty. and introduces one of the deepest mysteries in cosmology. According to quantum field theory, the framework that combines quantum mechanics with special relativity, every type of particle is an excitation of an underlying field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks, neutrinos, and all other particles correspond to their own fields. These fields exist everywhere, filling all of space, even when no particles are present. The vacuum is the lowest energy state of these fields. But lowest energy does not mean zero energy. Heisenberg's uncertainty principle prevents fields from being perfectly still. Even in their ground state, fields must fluctuate, their values oscillating around an average. These quantum fluctuations are not merely theoretical abstractions, they have measurable consequences. One of the most famous is the Casimir effect, discovered in 1948. When two uncharged metal plates are placed very close together in a vacuum, they experience an attractive force. This happens because the quantum fluctuations of the electromagnetic field are restricted between the plates. Only certain wavelengths fit in the gap, while outside the plates, all wavelengths are allowed. The imbalance in fluctuations creates a pressure that pushes the plates together. The Casimir effect has been measured experimentally, confirming that the vacuum is not empty but seething with electromagnetic activity. These vacuum fluctuations also affect the properties of particles. In quantum electrodynamics, virtual particles, pairs of particles and antiparticles can briefly appear, borrow energy from the vacuum, and then annihilate, disappearing as quickly as they came. These virtual particles influence the behavior of real particles, contributing to measurable quantities like the anomalous magnetic moment of the electron. The agreement between theoretical predictions and experimental measurements is astonishing, sometimes matching to more than 10 decimal places. The vacuum's activity is real and quantifiable, but there's a problem. If we try to calculate the total energy of the vacuum by summing the contributions from all possible quantum fluctuations across all fields, we get an absurdly large number, roughly 120 orders of magnitude larger than what we observe. This is the cosmological constant problem, one of the most severe mismatches between theory and observation in all of physics. Naively, the vacuum should have enough energy to curve spacetime so dramatically that the universe could not exist as we know it. Yet the observed vacuum energy, inferred from the accelerated expansion of the universe, is extraordinarily small, not zero, but close to it. This small but non-zero vacuum energy is what we associate with dark energy, the mysterious component driving cosmic acceleration. If dark energy is indeed vacuum energy, then the cosmological constant represents the inherent energy density of empty space. As the universe expands, more space comes into existence, and with it, more vacuum energy, creating a repulsive gravitational effect that accelerates expansion. The problem is explaining why the vacuum energy is so small when quantum field theory predicts it should be enormous. Something must be cancelling out the contributions from different fields with extraordinary precision, but we don't know what or why. One possibility is supersymmetry, a hypothetical symmetry that pairs every known particle with a superpartner of different spin. In supersymmetric theories, the vacuum energy contributions from bosons, particles with integer spin, and fermions particles with half-integer spin have opposite signs, and could cancel each other out almost completely. But supersymmetry, if it exists, must be broken at the energy scales we can probe, since we haven't observed any superpartners, and even with supersymmetry, achieving the precise cancellation needed to match observations requires fine-tuning so extreme it seems contrived. Another approach is the anthropic principle, which suggests that we might live in a multiverse where different regions of space have different values of the vacuum energy. In most of these regions, the vacuum energy is either so large and positive that structures never form, or so negative that space collapses immediately. We observe a small vacuum energy because only in such regions can galaxies, stars, and life exist. This explanation is philosophically unsatisfying to many physicists because it trades a why question for a selection effect, but it remains a possibility taken seriously in some theoretical circles. Vacuum energy also connects to the Higgs field, which permeates all of space and gives particles their masses. The discovery of the Higgs boson in 2012 confirmed that this field has a non-zero value, even in the vacuum, a phenomenon called spontaneous symmetry breaking. The Higgs field's vacuum expectation value determines the masses of fundamental particles. If the Higgs field had a different value, particles would have different masses. Chemistry would work differently, and life might not be possible. The vacuum structure, shaped by the Higgs field and perhaps other fields, is essential to the properties of matter. Quantum fields and vacuum energy also play a role in cosmology beyond dark energy. During the first moments after the Big Bang, a field, sometimes called the inflaton, might have driven a period of exponential expansion called cosmic inflation. This rapid expansion would have smoothed out the universe's initial irregularities and stretched quantum fluctuations to cosmic scales, creating the seeds of galaxies' large-scale structure. Inflation requires a vacuum energy-like component that dominated briefly before decaying into matter and radiation. The physics of vacuum fields, though still speculative in this context, might explain the universe's large-scale uniformity and structure. Even the stability of the vacuum is a question. Our current vacuum might not be the lowest energy state, it could be a false vacuum. Metastable but not truly stable. If so, a quantum fluctuation could trigger a transition to a lower energy, true vacuum, creating a bubble that expands at the speed of light, destroying the current structure of spacetime and particles within it. This scenario, while speculative and not supported by current observations, illustrates how deeply the properties of the vacuum affect the universe's existence and stability. The revelation of quantum fields and vacuum energy transforms our understanding of nothingness. Empty space is not a blank stage on which events occur. It's an active participant, filled with fields, fluctuations, and energy. The vacuum's properties determine the masses of particles, influence their interactions, and might drive cosmic expansion. It is both everywhere and invisible, both powerful and subtle, shaping reality in ways we're only beginning to understand. In the quantum vacuum, we see that power can be intrinsic to existence itself, woven into the fabric of space-time, present in every cubic centimeter of the universe, silent but essential, foundational but mysterious. All the structures we see in the universe, galaxies, stars, planets, atoms, originated from a beginning so hot, so dense, and so energetic that it challenges our imagination. This beginning is called the Big Bang, and it represents not just the start of matter and energy, but the start of space and time themselves. It is the ultimate expression of power in the cosmos, the moment when everything we know came into existence, when the universe transitioned from a state of unimaginable concentration to the vast, expanding reality we observe today. The Big Bang is not an explosion in space, but an expansion of space. In the earliest moments, the universe was not empty space containing matter. It was matter and energy compressed into an extraordinarily small, hot, and dense state. As time progressed, space itself expanded, carrying matter and energy along with it. This expansion continues today, observable in the redshift of distant galaxies, each one receding from us as space stretches between us. Evidence for the Big Bang comes from multiple sources. Edwin Hubble's discovery in the 1,920 seconds that galaxies are moving away from us, with more distant galaxies receding faster, suggested that the universe is expanding. Extrapolating backward, this expansion implies that everything was once much closer together. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, a faint, uniform glow of radiation coming from all directions. This radiation is the cooled remnant of the Big Bang's intense heat. photons that have been travelling since the universe was only 380,000 years old, stretched by expansion into microwaves. The abundance of light elements hydrogen, helium, and traces of lithium also matches predictions from Big Bang nucleosynthesis. In the first few minutes after the Big Bang, when the universe was hot enough for nuclear fusion but cool enough for nuclei to survive, protons and neutrons combined to form these elements in specific ratios. Observations of the universe's elemental composition match these predictions remarkably well, providing independent confirmation of the Big Bang model. But what happened in the very first moments? Our current understanding can take us back to fractions of a second after the Big Bang, but the very beginning, the first 10 to the negative 43 seconds, the Planck epoch remains beyond our grasp. At such extreme temperatures and densities, quantum gravitational effects dominate, and we lack a theory that can describe them. Was there a singularity, a point of infinite density, or did quantum effects smooth the beginning into something finite? Did time itself have a starting point, or did it emerge from a timeless quantum state? These questions remain open. One widely accepted idea is cosmic inflation, a brief period of exponential expansion that occurred in the first fraction of a second. Driven by a hypothetical field called the inflaton, inflation would have stretched the universe by an enormous factor in an incredibly short time, smoothing out initial irregularities and making the universe remarkably uniform. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating tiny density variations that later grew into galaxies and clusters. Inflation explains many features of the universe, its flatness, uniformity, and large-scale structure, but the details remain speculative. After inflation, the universe was filled with a hot, dense plasma of particles and radiation. For the first 380,000 years, photons scattered constantly off free electrons, keeping the universe opaque. As the universe cooled, electrons and protons combined to form neutral hydrogen atoms in a process called recombination. This allowed photons to travel freely for the first time, creating the cosmic microwave background we detect today. This moment marks the transition from an opaque to a transparent universe, and the photons from that time carry a snapshot of the cosmos in its infancy. Over hundreds of millions of years, gravity pulled matter into denser regions. These early stars, made only of hydrogen and helium, lived fast and died young, exploding as supernovae and enriching the universe with heavier elements. Successive generations of stars and galaxies formed, building the structures we observe today. The Big Bang set the initial conditions, the matter, energy, and expansion rate that have shaped the universe's entire history. The Big Bang also represents the origin of all the energy in the universe. Every photon, every particle, every bit of kinetic and potential energy traces back to that initial state. The energy was not created in the Big Bang, it was already present in that first moment, concentrated in a form we don't fully understand. Since then, it has transformed, diluted by expansion, converted into matter and radiation, locked into stars and galaxies, but never increasing or decreasing in total amount, only changing form. In terms of power, the Big Bang is unparalleled. In the first moments, energy densities reached values near the Planck scale. Temperatures exceeded 10 to the 32 degrees Kelvin. The universe expanded and cooled at rates that dwarf anything we observe today. Every cubic centimetre of space contained more energy than entire stars would later radiate in their lifetimes. The power was not concentrated in one location, it was everywhere, filling all of space because space itself was part of the event. The Big Bang also raises philosophical questions. What, if anything, came before? If time itself began at the Big Bang, the question, what happened before, might be meaningless, like asking what's north of the North Pole. Some theories propose a cyclic universe, where Big Bangs and crunches repeat endlessly. Others suggest a multiverse, where our Big Bang is just one bubble in a vast, ever-expanding collection. Still others invoke quantum mechanics, proposing that the universe emerged from a quantum fluctuation, a probabilistic event that requires no prior cause. None of these ideas are proven, but they reflect the deep mystery of cosmic origins. Despite the unknowns, the Big Bang framework has been extraordinarily successful. It explains the expansion, the cosmic microwave background, the abundance of elements, and the formation of structure. It provides a timeline for the universe's history, from fractions of a second after the beginning to the present, 13.8 billion years later. It has transformed cosmology from speculation into a precision science, with measurements and predictions tested against observation. The Big Bang's first burst was not just the most powerful event in the universe, it was the event that made the universe. It was the origin of space, time, matter, energy, and all the structure we observe. It set the initial conditions for everything that followed, from the formation of atoms, to the evolution of galaxies, to the emergence of life. In reflecting on the Big Bang, we see power not just as energy released, but as creation itself, the transformation of potentiality into actuality, the beginning of existence as we know it. It is the ultimate expression of cosmic power, the foundation upon which all other phenomena rest. We have wandered through the cosmos, from the smallest particles to the largest structures, from the beginning of time to the distant future, asking one question: what is the most powerful thing in the universe? Along the way, we have seen gravity shaping galaxies, electromagnetism creating light and structure, nuclear forces binding atoms and powering stars, dark matter providing invisible scaffolding, and dark energy driving cosmic acceleration. We have witnessed supernovae exploding with the energy of billions of suns, black holes warping spacetime beyond recognition, and the Big Bang itself giving birth to everything. And now, as we prepare to rest, we can reflect on what this journey has revealed. The answer, it turns out, is not singular. There is no one thing that dominates all others in every sense. Power in the universe takes many forms, each supreme in its own domain. Gravity is weak between particles, but shapes the cosmos at large scales. Electromagnetism is strong and versatile, but largely cancels out beyond atoms. The strong nuclear force is the strongest interaction, but confined to the smallest distances. The weak force enables transformations that make stars shine and elements form. Dark matter outweighs everything visible. Dark energy dominates the universe's fate. The Big Bang was the most concentrated burst of energy. Black holes represent gravity's ultimate expression. What we discover is that power is contextual. It depends on scale. What matters at atomic distances differs from what matters across billions of light years. It depends on time, brief explosions, versus sustained energy output. It depends on influence, direct force, versus subtle shaping of structure. Each phenomenon we've explored is powerful in its own way, and trying to crown a single champion misses the point. The universe is not ruled by one force or one event, but by the interplay of many, each contributing to the whole. There's also the distinction between visible and invisible power. Supernovae are dramatic, obvious displays of energy, impossible to miss when they occur, but dark matter and dark energy, completely invisible, together make up 95% of the universe's content and determine its structure and fate. The most powerful components are often the least apparent, working quietly, shaping everything without fanfare. This teaches us that power need not be loud or bright to be profound. We also see that power can mean persistence as much as intensity. A gamma-ray burst might release more energy in 10 seconds than the sun will emit in its lifetime, but the sun has shone steadily for nearly 5 billion years and will continue for another 5 billion. Which is more powerful, the brief flare or the enduring engine? Both have their place. The universe contains both extremes and everything in between. In human terms, this exploration connects us to the cosmos in unexpected ways. The atoms in our bodies were forged in stars. The energy that sustains us comes from sunlight, ultimately from fusion. The forces that hold our molecules together are electromagnetic. The expansion of the universe is driven by dark energy. Even the vacuum of space, seemingly empty, is filled with quantum activity that shapes reality at fundamental levels. We are not separate from these cosmic powers, we are part of them, products of billions of years of stellar evolution, galactic dynamics, and cosmic expansion. Understanding power in the universe also highlights the limits of our knowledge. We don't know what dark matter is. We don't know what dark energy is. We don't have a theory that unifies quantum mechanics and gravity. We don't know what happened at the very beginning of the Big Bang, or what lies at the center of a black hole. The most powerful phenomena often coincide with the deepest mysteries. This humility is appropriate. The universe does not yield its secrets easily. Yet the search for understanding is itself a kind of power, the human capacity for curiosity, reason, and exploration. We've built instruments that detect gravitational waves from colliding black holes billions of light years away. We've measured the cosmic microwave background with extraordinary precision. We've created mathematical frameworks that describe phenomena from quantum fields to cosmic expansion. We've sent spacecraft beyond the solar system and peered back to see the universe's earliest moments in ancient light. This intellectual and technological achievement represents a different kind of power, one unique to conscious beings capable of asking questions and seeking answers. There's also beauty in the patterns we've uncovered. The same physical laws apply everywhere, from the smallest scales to the largest. The forces that govern atoms also govern galaxies. The energy released in a supernova follows the same conservation principles as a ball rolling down a hill. This universality suggests an underlying simplicity, an elegance to nature that makes the universe comprehensible despite its vastness and complexity. As we close this journey, we might ask, does it matter which thing is most powerful? Perhaps the value lies not in ranking phenomena, but in seeing them all in understanding how gravity, electromagnetism, nuclear forces, dark components, quantum fields, and cosmic expansion work together to create the universe we inhabit. Each is essential. Remove any one, and reality would be unrecognizable. Gravity without electromagnetism would have no atoms. Stars without the weak force couldn't burn. A universe without dark energy would evolve differently, perhaps not allowing galaxies to form as they have. The most powerful thing in the universe might be the whole, the integrated system of forces, fields, particles, and expansion that has produced stars, galaxies, planets, and life. It's the interplay, the balance, the dance of opposing tendencies that creates structure and complexity. Gravity pulls together, dark energy pushes apart. Fusion releases energy. Entropy spreads it thin. The strong force binds. Electromagnetic repulsion separates. In this dynamic tension, the universe finds its form. And what of the future? The universe will continue to evolve, shaped by these same powers. Dark energy will drive expansion faster and faster. Stars will eventually exhaust their fuel. Black holes will evaporate over unimaginable timescales. The cosmos will cool, thin, and approach a state of maximum entropy. But that is trillions of years away. For now, we live in a time of stars and galaxies, of structure and complexity, of light and warmth. We are witnesses to the universe in its active, vibrant phase, powered by forces and energies that reach back to the Big Bang and forward to a distant, quiet future. As you lie here, drifting towards sleep, you can carry this perspective with you. You are part of a universe filled with power in countless forms, gravity shaping your orbit around the sun, electromagnetism holding your body together, nuclear forces within every atom, dark components surrounding and permeating everything, quantum fields fluctuating even in empty space. The same energies that power stars flow through you in quieter forms. The same laws that govern galaxies govern your cells. The question, what is the most powerful thing in the universe, becomes not a search for one answer, but an invitation to see the whole, to appreciate gravity and light, fusion and decay, visible and invisible, brief and eternal, Creation and entropy. Each is part of the story. Each contributes to the cosmic symphony. And in understanding them, even imperfectly, we connect to something larger than ourselves, an ancient, ongoing process that began with the Big Bang and continues in every moment, in every breath, in every thought. Thank you for wandering through this cosmic exploration with me tonight. If this journey brought you calm, curiosity, or a gentle path toward rest, you can return whenever you wish. The universe's powers will still be there, shaping, sustaining, surrounding everything. For now, let the vastness hold you, let the quiet settle in, and let sleep come as naturally as stars forming in the depths of space. Good night.